So, here's something worth thinking about as you settle in tonight. Right now, inside your chest, something extraordinary is happening. Without you thinking about it, without you asking it to, a fist-sized muscle is squeezing and releasing, pushing blood through a network of vessels so vast that if you could somehow unravel every artery, vein and capillary in your body and lay them end to end, they would stretch something like 60,000 miles. That is enough to wrap around the entire planet Earth more than 2 times. And the pump doing all that work weighs less than a pound, maybe 11 ounces, give or take. It started beating before you were born, somewhere around 3 weeks after you were conceived, before your mother probably even knew you existed. And it has not stopped since, not once, not for a single second. It is beating right now as you lie there listening to this, and it will keep beating while you fall asleep, and it will still be going when you wake up tomorrow. Over the course of an average lifetime, that is something like 2.5 billion beats. No rest days, no maintenance windows, just continuous, rhythmic, astonishing work. Think about that number for a moment. 2.5 billion cycles of contraction and relaxation. 2.5 billion times that this soft, living tissue has squeezed and released, without ever wearing out, without ever needing replacement parts, without ever stopping for a tune-up. Every single one of those beats had to happen in exactly the right sequence, at exactly the right time, with exactly the right force, or the whole system would have failed. And it did not fail. It has not failed. It is not failing right now. Now, here is the thing that makes this truly remarkable. For most of human history, nobody really understood how any of this worked. People knew the heart was important, obviously. You did not need a medical degree to notice that when someone's heart stopped, they died. But the actual mechanics of it, the engineering of the thing, how it moves blood, why it beats, what all those chambers and valves are actually doing, that took thousands of years to figure out. The ancient Egyptians, who were among the first to write down their ideas about the heart, got some things surprisingly right and other things spectacularly wrong. They believed the heart was the seat of the soul, the center of intelligence, the core of a person's identity. Which is why during mummification, they carefully preserved the heart inside the body, but scooped the brain out through the nose with a hook and threw it away. The brain to them was basically stuffing, useless tissue. The heart was everything. And in a way, you can understand why they thought that. You can feel your heart. When you are scared, it pounds. When you are in love, it races. When you are calm, it slows. The brain just sits up there, silently, doing its thing, without any obvious sensation. So the Egyptians looked at the heart and said, that is where the person lives. The Greeks took it further. Aristotle, around 350 BCE, studied animal hearts by dissection and noticed that the heart has chambers and that large vessels connect to it. But he also believed the heart was the source of heat in the body, like a furnace, and that the lungs existed primarily to cool the blood down. Think of it like a radiator for an engine. The heart generates heat. The blood carries that heat around, and the lungs act as a cooling system. It is wrong, but it is a beautifully logical system if you are working from first principles without any way to measure what is actually happening at a cellular level. Then came Galen, born around 129 CE, who was the physician to Roman gladiators. which gave him an unusual opportunity to see inside living human bodies through wounds and injuries. He later became personal physician to the Roman Emperor Marcus Aurelius. Galen wrote hundreds of texts describing anatomy in extraordinary detail, and because of his reputation and the sheer volume of his work, his ideas became gospel for over 1,300 years. European and Islamic medicine treated Galen's writings as essentially sacred, not to be questioned. And here is what Galen got wrong about the heart. He believed that blood was produced in the liver from the food you ate. The liver, in his model, was the blood factory. It took nutrients from digestion, converted them into blood, and then that blood flowed outward through the veins to nourish the body. But the crucial part is that he thought the blood moved in a kind of tidal flow, out to the tissues, consumed there, and then more blood made in the liver to replace it. There was no circuit, no loop. Blood did not come back. It was manufactured, sent out, used up, and that was it. Galen knew there were two types of vessels, arteries and veins. He could see that. But he thought they were two completely separate systems carrying two different kinds of blood. Venous blood made in the liver, dark and thick, carried nourishment. Arterial blood, which was brighter red, carried something he called pneuma, vital spirit, which it picked up from the lungs. And here is where it gets really interesting. Galen knew that the heart had a thick wall between the left and right sides. That wall is called the septum, and he needed to explain how blood got from the right side to the left side, because in his model, some venous blood had to cross over to mix with air from the lungs and become arterial blood. So he proposed that the septum had tiny invisible pores, holes so small you could not see them, that allowed blood to seep through from right to left. Those invisible pores do not exist. The septum is solid, but Galen said they were there, and for 1,300 years nobody with enough authority challenged him on it. Think about what that means. For over 1,000 years, the entire Western understanding of how blood moves through the body was built on a wall with imaginary holes in it. Now, it was not that nobody noticed problems with Galen's model. A few people did. Ibn al-Nafis, a Syrian physician working in Cairo around 1242, wrote a commentary on one of Galen's texts and quietly described what we now call pulmonary circulation. The idea that blood goes from the right side of the heart to the lungs, picks up air there, and then comes back to the left side of the heart through the pulmonary veins. He explicitly said, "The septum is solid, there are no pores, and blood must travel through the lungs to get from one side of the heart to the other." He was completely right, and almost nobody in Europe read his work for centuries. His insight was essentially lost, rediscovered only in the 20th century by historians going through old manuscripts. Imagine being that right, that early, and having it just vanish into a library shelf. In Europe, the person who started to crack things open, sometimes literally, was Andreas Vesalius, born in Brussels in 1514. Vesalius was a young anatomy professor at the University of Padua, and he did something radical. He actually performed his own dissections. This sounds obvious, but at the time, anatomy lectures typically involved a professor sitting in a raised chair reading from Galen, while a barber surgeon did the actual cutting down below. The professor never touched the body. Vesalius changed that. He got his hands dirty. He cut. He looked. And he started finding things that did not match what Galen had written. In 1543, Vesalius published De Humani Corporis Fabrica, one of the most important books in the history of medicine. It is a gorgeous book, full of detailed anatomical illustrations, showing the body in dramatic poses, muscles peeled back, skeletons leaning thoughtfully against pedestals. And in it, Vesalius described the septum of the heart and noted carefully, diplomatically, that he could not find those pores Galen had described. He did not come right out and say Galen was wrong. That would have been career suicide, and possibly actual suicide. But he planted the seed of doubt. He wrote something along the lines of, "The septum is as dense and thick as the rest of the heart," and he could not understand how even the smallest amount of blood could pass through it. That is a very polite way of saying, "I think the old master made this up." But Vesalius did not have the full answer. He could see the problem, but he could not yet describe the solution. That would take another generation, and it would take a man who was willing to go much further. A man named William Harvey. Harvey was born in Folkestone, England, in 1578. He studied at Cambridge, then travelled to Padua, the same university where Vesalius had taught, to study under a brilliant anatomist named Hieronymus Fabricius. And Fabricius had discovered something curious. He had found that veins contain small flap-like structures, valves, that allow blood to flow in only one direction. Fabricius did not fully understand what these valves meant. He thought they were there to slow blood down, to prevent it from pooling in the extremities. But Harvey looked at those valves and started thinking. If blood can only flow one way through the veins, and that direction is always toward the heart, then Galen's tidal model does not work. Blood is not flowing out and being consumed, it is coming back. Harvey spent years on this. He dissected animals, deer, frogs, fish, snakes, dogs. He tied off blood vessels and watched what happened. He measured. And this is where Harvey did something that was genuinely revolutionary. Something that sounds simple, but changed everything. He did the math. He estimated how much blood the heart pumps with each beat. Roughly 2 ounces, he figured. And then he multiplied that by the number of beats per half hour. And the number he got was enormous. Far more blood than the body could possibly manufacture from food in that time. The liver could not be making that much blood from scratch. It was physically impossible. The only explanation that made sense was that the same blood was going around and around in a circle. A circuit. The blood leaves the heart, travels through the arteries, reaches the tissues, comes back through the veins, returns to the heart, and goes around again. Harvey published his findings in 1628 in a slim book called Exercitatio Anatomica, De Motu Cordis et Sanguinis in Animalibus, an anatomical exercise on the motion of the heart and blood in animals. He laid out the case for circulation, clearly, methodically, and with devastating logic. The heart, Harvey argued, is a pump, not a furnace, not a spiritual organ, not a mysterious source of vital heat. A pump, a mechanical device that moves fluid through pipes. It was an engineering insight as much as a medical one, and it was a radical reframing. Because once you think of the heart as a pump, everything else follows. You can ask engineering questions about it. How much volume does it move? What is the pressure? Where is the resistance? What happens when part of the system fails? Harvey gave medicine a mechanical framework, and we are still using it. Every time a cardiologist talks about cardiac output or ejection fraction, or vascular resistance. They are speaking a language that traces back to Harvey, standing in a cold room in London, counting heartbeats and doing arithmetic. Now, the reaction to Harvey's work was mixed. Some physicians were genuinely excited. They could see the elegance of the argument, the way it swept away centuries of confusion and replaced it with something clean and testable. But a lot of the medical establishment pushed back hard. Harvey's contemporaries had built their entire careers on Galenic medicine. Their treatments, their theories, their reputations, all of it rested on the idea that the liver made blood and the body consumed it. If Harvey was right, a huge portion of established medical practice was based on a fantasy. That is threatening. People do not give up their worldview easily, especially when their livelihood depends on it. Harvey was called a crackpot by some. His medical practice suddenly suffered for a while. There is a story, possibly apocryphal, that people started avoiding him as a physician because they thought his ideas were too radical, too strange. He reportedly said that no man over 40 accepted his theory. The young doctors got it. The old guard resisted, which is a pattern you see over and over in the history of science. Paradigm shifts do not happen because everyone reads the new paper and says, "Oh, you are right, I was wrong." They happen because a new generation grows up with the new idea already in place, and the old generation eventually retires, or to put it bluntly, dies. Harvey lived long enough to see his ideas gain real traction, though. He died in 1657, and by then the tide was turning. But here is the thing Harvey could not solve. He knew blood went from arteries to veins somehow. It had to. His whole model depended on it. The blood leaves the heart through the arteries and then somehow gets into the veins to flow back. But how? Harvey could not see the connection. With the naked eye, arteries seem to just end. They get smaller and smaller and then disappear into the tissue. And the veins start up seemingly from nowhere. Harvey believed there must be tiny connections. He called them porosities in the flesh. But he could not prove it. He could not see them. Nobody could. The technology did not exist yet. 4 years after Harvey died, in 1661, an Italian physician named Marcello Malpighi pointed a microscope at the lung of a frog and saw something no human being had ever seen before. Capillaries. Tiny, impossibly thin blood vessels connecting the smallest arteries to the smallest veins. The missing link. The piece Harvey needed but could never find. For the first time, the entire circuit was visible. Heart to arteries, arteries to capillaries, capillaries to veins, veins back to heart. A closed loop. Harvey's theory confirmed at the microscopic level. So now, tonight, as you lie there, you know something that the greatest minds of antiquity did not. You know that the fist-sized muscle in your chest is not a furnace or a spiritual organ or a mysterious source of heat. It is a pump. A remarkably engineered pump. And what I want to do in this video is walk you through how that pump works. Not in a rush, not skimming over the details, but slowly, carefully, the way you would explain something to someone you really liked at the end of a long evening. We are going to trace the path of a single drop of blood from the moment it leaves the heart to the moment it returns. We are going to understand how the heart creates the pressure to push blood through 60,000 miles of vessels. We are going to see how the 4 chambers work together, how the valves open and close in perfect sequence, how the electrical system generates its own rhythm without any signal from the brain. We are going to understand why there are 2 separate circuits, one for the lungs and one for the rest of the body, and how the heart manages both at the same time. We are going to explore how arteries handle high pressure, how capillaries exchange oxygen and nutrients, and how veins manage to return blood to the heart against the pull of gravity. And here is the question that will guide us through all of this. How does a soft, living organ weighing less than a pound manage to function as the most reliable pump in the known universe, cycling 2.5 billion times without failing, without stopping, without a single conscious instruction from you? How does it do it? That is what we are going to find out together.
Before we can understand how the heart works, we have to understand the problem it was designed to solve. And to understand that problem, we have to start with something much smaller. We have to start with your cells. Right now, your body contains roughly 30 to 40 trillion cells. That is 30,000 billion individual living units, each one carrying out thousands of chemical reactions every second, each one consuming energy, each one producing waste. And every single one of those cells, from the neurons in your brain to the muscle fibers in your toes, needs two things to survive. It needs oxygen to burn fuel for energy, and it needs nutrients, like glucose and amino acids, to build and repair itself. And every single one of those cells also produces waste products that have to be removed. Carbon dioxide, lactic acid, urea, and other byproducts of metabolism that become toxic if they are allowed to accumulate. Now here is the problem. Your cells are not all sitting on the surface of your body where they can just grab what they need from the air and the food around you. Most of them are buried deep inside. The cells in your liver are surrounded by other cells. The cells in your brain are protected by the skull. The cells in your muscles are wrapped in layers of tissue. And the distance from the surface of your body to the deepest cells can be several inches. That might not sound like much, but for a molecule trying to get from the outside world to a cell deep inside, that distance is enormous. Think about it this way. If a single cell were the size of a person, the distance it would have to travel to get nutrients from the surface of the body would be like walking from New York to Los Angeles. And the only way molecules can move on their own without any help is through a process called diffusion, where they slowly drift from areas of high concentration to areas of low concentration. Diffusion works fine over microscopic distances. It is how a single-celled organism, like an amoeba, gets its oxygen. The amoeba is surrounded by water. Its entire surface is exposed to the environment, and oxygen just diffuses right in. But over distances larger than a fraction of a millimeter, diffusion becomes hopelessly slow. It would take hours for oxygen to reach the deepest cells, and by then, those cells would have died. So, nature faced a fundamental engineering problem. How do you deliver oxygen and nutrients to every cell in a large, complex, three-dimensional body, and remove waste products from those same cells fast enough to keep everything alive? The solution was a transportation system, a network of pipes that would carry a fluid containing oxygen and nutrients to every corner of the body, and then carry waste products back out. And at the center of that system, you would need a pump powerful enough to push that fluid through the entire network, maintaining enough pressure to overcome the resistance of all those narrow pipes and reach even the most distant cells. That pump is your heart, and the fluid it moves is blood. But here is the thing about this system that makes it so remarkable. The pipes are not rigid metal tubes, they are living tissue. The pump is not a mechanical device made of steel and plastic. It is a hollow muscle that beats continuously for decades. And the fluid it moves is not just water. It is a complex suspension of cells and proteins that carries oxygen, nutrients, hormones, immune cells, and clotting factors. To understand how the heart accomplishes this, we have to think about it like an engineer would. An engineer designing a pump for a building
would ask several basic questions. How much fluid needs to be moved? How much pressure is needed to overcome the resistance of the pipes?
What is the best way to create that pressure? And how do you make sure the fluid flows in the right direction and does not just slosh back and forth? The same questions apply to the heart. First, how much blood needs to be moved? Your heart pumps about 5 quarts of blood per minute at rest. That is roughly the entire volume of blood in your body every single minute. During exercise, that number can increase to over 8 gallons per minute. Over the course of a day, your heart pumps about 2,000 gallons of blood. Over a year, that is about 700,000 gallons. Over an average lifetime, your heart will pump enough blood to fill several Olympic-sized swimming pools. Second, how much pressure is needed? The resistance to flow in the blood vessels comes from their narrowness, especially in the tiny vessels called capillaries.
To overcome this resistance and push blood through all 60,000 miles of vessels in your body, the heart has to create significant pressure. When your left ventricle contracts, it generates a pressure of about 120 millimeters of mercury. That is enough pressure to push a column of mercury 120 millimeters high, or a column of water more than 5 feet high. And it has to maintain this pressure with every beat without interruption for your entire life. Now, here is where the engineering gets really interesting. The heart is not just one pump. It is 2 pumps working side by side. The right side of the heart pumps blood to the lungs. The left side of the heart pumps blood to the rest of the body. And these 2 pumps have very different requirements. The lungs are delicate structures. They do not need high pressure. Blood only needs about 25 millimeters of mercury to flow through the pulmonary circulation.
If the pressure were much higher, it would damage the fragile capillaries in the lungs. But the rest of the body has much higher resistance. Blood needs about 120 millimeters of mercury to reach the toes and the brain. So the left ventricle has to be much more powerful than the right. Its walls are 2 to 3 times thicker, and it generates roughly 4 times the pressure. This is why the heart is divided into left and right sides. It keeps the low-pressure pulmonary circuit separate from the high-pressure systemic circuit. If the same pump had to handle both, it would either overpressurize the lungs or underpressurize the body. By having 2 pumps in one, the heart solves this problem elegantly. The right side handles the low-pressure lung circuit. The left side handles the high-pressure body circuit. And both pumps beat simultaneously, in perfect coordination. Now, let us look at the structure of this double pump. Each side of the heart has 2 chambers. An upper chamber called an atrium, which receives blood returning to the heart, and a lower chamber called a ventricle, which pumps blood out of the heart. The atrium is thin-walled because it only needs to push blood a short distance into the ventricle. The ventricle has thick, muscular walls because it has to generate enough pressure to push blood through the entire circuit. The right atrium receives blood returning from the body through 2 large veins, the superior vena cava and the inferior vena cava. The superior vena cava brings blood from the head, neck, and arms. The inferior vena cava brings blood from the lower body. This blood is low in oxygen and high in carbon dioxide, and it appears dark red. From the right atrium, blood passes through the tricuspid valve into the right ventricle. The right ventricle pumps this blood through the pulmonary valve into the pulmonary artery, which carries it to the lungs. In the lungs, the blood releases carbon dioxide and picks up fresh oxygen. It then returns to the left atrium through the pulmonary veins. The left atrium receives this oxygen-rich blood from the lungs.
From the left atrium, blood passes through the mitral valve into the left ventricle. The left ventricle, the most powerful chamber in the heart, pumps this blood through the aortic valve into the aorta, the largest artery in the body. From the aorta, the blood flows through a branching network of arteries to every organ and tissue in the body. And here is what is crucial to understand about this entire system. It is a closed loop. Blood never leaves the network of vessels. It just keeps circulating. The same blood that left the heart through the aorta will eventually return to the heart through the vena cava, then go to the lungs, then return to the left atrium, and then be pumped out again. The journey never ends. The system is continuous.
And it must be continuous, because if it stopped for even a few minutes, the cells of your body would begin to die from lack of oxygen. Now, let us think about the direction of flow. Blood has to flow in one direction only, from the heart to the arteries, to the capillaries, to the veins, and back to the heart. It cannot flow backward. If blood flowed backward, the system would not work. The heart would be trying to pump blood out while blood was also flowing back in, and the pressure would drop. To prevent this, the heart and veins contain specialized structures called valves. There are 4 valves in the heart. The tricuspid valve between the right atrium and right ventricle, the mitral valve between the left atrium and left ventricle, the pulmonary valve between the right ventricle and the pulmonary artery, and the aortic valve between the left ventricle and the aorta. These valves open and close passively, driven by pressure differences. When the pressure behind a valve is higher than the pressure in front of it, the valve opens and blood flows through. When the pressure is higher in front, the valve closes and blocks the backward flow. This is what makes the heart a one-way pump. No matter what happens, blood always moves forward. The sequence of events that drives this flow is called the cardiac cycle. It consists of 2 phases: systole, when the heart contracts and pumps blood, and diastole, when the heart relaxes and fills with blood. During systole, the ventricles contract. The pressure inside them rises sharply. This forces the AV valves to close, preventing blood from flowing back into the atria. The pressure continues to rise until it exceeds the pressure in the pulmonary artery and the aorta. At that point, the pulmonary and aortic valves open, and blood is ejected into the circulation. During diastole, the ventricles relax. The pressure drops. The pulmonary and aortic valves close, preventing blood from flowing back into the ventricles. The AV valves open, and blood flows from the atria into the ventricles, filling them for the next beat. This cycle repeats roughly 70 times per minute at rest, faster during exercise, slower during sleep. And every single beat is coordinated by an electrical system that operates independently of the brain. The signal for each beat originates in a small cluster of specialized cells called the sinoatrial node, or SA node, located in the wall of the right atrium. These cells spontaneously generate electrical impulses at a regular rate. The impulses spread across the atria, causing them to contract. They then reach another cluster of cells called the atrioventricular node, or AV node, which delays the signal slightly to allow the atria to finish contracting before the ventricles begin. From the AV node, the signal travels down a bundle of specialized fibers called the bundle of His, then branches into the right and left bundle branches, and finally spreads through the walls of the ventricles via a network of fibers called Purkinje fibers. This coordinated spread of electrical activity ensures that the heart contracts in a smooth, efficient sequence. So, let us pause here and just look at what we have established. The heart is a double pump. 2 pumps in one, working side by side, one for the lungs and one for the body. Each pump has an atrium and a ventricle. Valves keep the blood flowing in one direction. An internal electrical system coordinates the contractions.
And all of this happens automatically, without conscious thought, every second of every day. But we have only just begun, because the real story is what happens when we follow the blood out of the heart and through the arteries, capillaries and veins. That is where the most important work happens. That is where oxygen and nutrients are delivered to your cells and where waste products are removed. That is where the blood actually does its job. The heart is just the engine. The vessels are where the work gets done. And in the next chapter, we are going to follow the blood on that journey, from the moment it leaves the left ventricle until it returns to the right atrium, tracing every step of the way. We will see how arteries handle high pressure, how capillaries allow exchange between blood and tissues, and how veins manage to get blood back to the heart against the pull of gravity. We will understand how the body regulates blood flow to different organs, sending more blood to muscles during exercise and more to the stomach after a meal. We will see how the same system that delivers oxygen to your brain also removes carbon dioxide from your lungs.
And we will understand why this system is so fundamental to life that it is one of the first things to develop in an embryo and one of the last things to stop working when you die. But before we get to all of that, let us just sit with what we have already learned. Your heart beats about 100,000 times a day, more than 35 million times a year, more than 2.5 billion times in an average lifetime. It never stops. It never takes a break. It never goes on vacation. And it does all of this using only the fuel it gets from the blood it pumps. It is, quite simply, one of the most remarkable pumps ever designed. And the next time you feel your pulse, remember that what you are feeling is the result of an engineering solution that took nature billions of years to refine. A solution so effective that even after centuries of study, we are still discovering new ways it works.
Now that we understand the basic structure of the heart, let us follow the blood on its journey. Let us trace the path of a single drop of blood from the moment it leaves the left ventricle until it returns to the right atrium. This is the systemic circulation, the part of the cardiovascular system that delivers oxygen and nutrients to every tissue in your body. When the left ventricle contracts, it ejects blood into the aorta. The aorta is the largest artery in your body, about 1 inch in diameter in a typical adult, and its walls are incredibly strong. They have to be, because the pressure inside the aorta immediately after the left ventricle contracts is about 120 millimeters of mercury. That is enough pressure to push a column of mercury more than 4.5 feet high. If the aorta were made of anything less durable than its triple-layered wall of elastic and connective tissue, it would burst. But the aorta is not just a pipe. It is an elastic reservoir. When the left ventricle ejects blood into it, the aorta stretches, absorbing some of the force of the ejection. Then, during diastole, when the ventricle is relaxing, the elastic walls of the aorta recoil, pushing the blood forward into the arteries. This elasticity is what turns the intermittent spurts of blood from the heart into a continuous flow. Without it, the blood would only move during systole, and your organs would not receive a steady supply of oxygen. From the aorta, the blood flows into a branching network of arteries. The aorta itself has several major branches. The coronary arteries, which we will talk about later, supply the heart muscle itself. The brachiocephalic artery, the left common carotid artery, and the left subclavian artery supply the head, neck, and arms. The descending aorta runs down through the chest and abdomen, giving off branches to the organs of the trunk and the legs. As the arteries get farther from the heart, they get smaller. They branch and branch again, like a river splitting into smaller streams. Eventually, they become arterioles, which are so small that you cannot see them without a microscope. The arterioles are the resistance vessels of the circulation. They have a thick layer of smooth muscle in their walls, and by contracting or relaxing that muscle, they can change their diameter significantly. This ability to change diameter is one of the most important mechanisms your body has for controlling blood flow. Think about what happens when you exercise. Your muscles are working hard, consuming oxygen rapidly, producing carbon dioxide and other waste products. The arterioles supplying those muscles dilate, widening their diameter. This reduces the resistance to flow, allowing more blood to reach the muscles. At the same time, arterioles supplying organs that are less active, like your stomach or kidneys, constrict, redirecting blood to where it is needed most. This is called redistribution of blood flow, and it is a continuous process happening in your body right now, adjusting to your changing needs without you ever having to think about it. From the arterioles, blood flows into the capillaries, and here, everything changes. Capillaries are the smallest blood vessels in your body. They are so small that red blood cells have to squeeze through them single file. Their diameter is only about 5 to 10 micrometers, which is just slightly wider than a red blood cell. And their walls are incredibly thin, only a single layer of endothelial cells with no smooth muscle at all. This is where the real work of circulation happens. The walls of the capillaries are thin enough that oxygen, carbon dioxide, nutrients, and waste products can diffuse through them. In the tissues, oxygen diffuses from the blood in the capillaries into the cells, while carbon dioxide diffuses from the cells into the blood. Glucose and amino acids leave the blood and enter the cells. Urea and other waste products leave the cells and enter the blood. The exchange is driven by differences in concentration. The blood arriving at the capillaries from the arterioles has a high concentration of oxygen and a low concentration of carbon dioxide. The tissues, which are constantly consuming oxygen and producing carbon dioxide, have the opposite pattern. So oxygen moves from blood to tissue, and carbon dioxide moves from tissue to blood. The same principle applies to nutrients and waste products. But the capillary exchange is not just about diffusion. There is also a process called filtration, driven by pressure. At the arterial end of a capillary, the blood pressure is high enough to push fluid out of the capillary into the tissue space. This fluid contains water, ions, and small molecules, but not proteins or cells, which are too large to pass through the capillary wall.
At the venous end of the capillary, the pressure has dropped, and the osmotic pressure created by proteins in the blood pulls fluid back into the capillary. This balance between filtration and reabsorption is crucial for maintaining the fluid balance in your tissues. If more fluid is filtered out than is reabsorbed, you get edema, swelling due to fluid accumulation in the tissues. Now, here is something interesting about the capillaries. Even though each individual capillary is tiny, the total number of capillaries in your body is enormous, somewhere between 10 and 40 billion. And the total surface area of all these capillaries is immense, roughly 600 square meters, about the size of a tennis court. This vast surface area is what makes efficient exchange possible. It ensures that every cell in your body is within a few hundred micrometers of a capillary. But here is the trade-off. Because the capillaries are so numerous and so tiny, the blood flow through them is very slow. The velocity of blood in the aorta is about 40 centimeters per second. In the capillaries, it drops to about 1 millimeter per second, 400 times slower. This slow flow is essential for exchange. It gives enough time for oxygen and nutrients to diffuse out of the blood, and for carbon dioxide and waste products to diffuse in. If blood rushed through the capillaries, the exchange would not happen efficiently. So, after the blood has passed through the capillaries, it is now depleted of oxygen and rich in carbon dioxide. It has given up most of its nutrients and picked up waste products.
It is dark red, almost blue, and it needs to get back to the heart to be pumped to the lungs for a fresh supply of oxygen. This is where the veins come in. The capillaries drain into small veins called venules, which then merge to form larger veins. The veins carry the blood back to the heart.
And here, the engineering challenges are different from the arteries. The pressure in the veins is very low, only about 5 to 10 millimeters of mercury. So the veins do not need thick walls. They are much thinner and more distensible than arteries. They can hold a large volume of blood at low pressure. But the low pressure in the veins creates a problem. How does blood get back to the heart when the pressure is so low? You are lying down now, so gravity is not working against you. But think about what happens when you stand up. The veins in your legs have to carry blood all the way up to your chest against the pull of gravity. The pressure in your veins is not high enough to do this on its own, so the body has evolved several mechanisms to help return blood to the heart. One is the muscle pump. When the muscles in your legs contract, they squeeze the veins, pushing blood upward. The veins contain one-way valves that prevent blood from flowing backward.
So each time your calf muscle contracts, it squeezes blood upward through a valve. When the muscle relaxes, the valve closes, preventing blood from falling back down. This is why moving your legs, even just flexing your feet, can help prevent blood from pooling in your lower body. Another mechanism is the respiratory pump. When you breathe in, the pressure in your chest decreases, while the pressure in your abdomen increases. This pressure difference helps draw blood from the lower body into the chest. And finally, the sympathetic nervous system can constrict veins, reducing their capacity and pushing blood back toward the heart. All of these mechanisms work together to ensure that blood returns to the heart at the same rate that the heart pumps it out. If venous return drops, the heart has less blood to pump, and cardiac output falls. If venous return increases, the heart pumps more blood. This is called the Frank-Starling mechanism, and it is one of the most important principles of cardiac function. The heart pumps whatever blood comes back to it. It does not generate pressure on its own. It responds to the volume of blood that fills it. So, let us recap the entire journey. Blood leaves the left ventricle through the aorta. It travels through increasingly smaller arteries and arterioles until it reaches the capillaries. In the capillaries, exchange occurs. Oxygen and nutrients leave the blood, and carbon dioxide and waste products enter. The blood then flows through venules and veins, using muscle pumps, respiratory pumps, and venous valves to return to the right atrium. From there, it will be pumped to the lungs, pick up oxygen, and return to the left atrium to start the journey again. This is the circle of life, as simple and as profound as that. Every cell in your body depends on this continuous flow, and every part of the system, from the thick walls of the aorta to the microscopic capillaries to the one-way valves in your leg veins, is perfectly adapted to its task. But the story does not end here, because the cardiovascular system is not just a passive network of pipes. It is an actively regulated system, constantly adjusting to your needs. When you run, your heart beats faster. When you eat, more blood flows to your stomach. When you are scared, your blood pressure rises. This regulation is carried out by the nervous system and by hormones, and understanding how this regulation works is the key to understanding many diseases, from high blood pressure to heart failure. In the next chapter, we will explore this regulation. We will see how the brain controls the heart, how hormones act on blood vessels, and how the body maintains blood pressure even when you stand up,
even when you lose blood, even when you exercise.
We will learn about the baroreceptor reflex, the renin-angiotensin system, and the role of the kidneys in regulating blood volume. We will understand why blood pressure is not a fixed number, but a carefully controlled variable that your body adjusts from moment to moment. And we will see how this system, so elegantly designed, can sometimes go wrong. How high blood pressure can damage arteries. How heart failure can result from a failing pump. And how understanding the physiology of the heart and circulation can lead to better treatments and longer lives. But for now, just think about that drop of blood. It started in the left ventricle, traveled through the aorta, the arteries, the arterioles, and the capillaries. It exchanged oxygen for carbon dioxide. It traveled through venules and veins, fighting gravity to return to the heart. And it did all of this in less than 1 minute. That is the journey of a drop of blood. And your heart sends millions of drops on this journey every single minute of every single day. The next time you feel your pulse, remember that you are feeling the result of an entire system working in perfect harmony. And remember that this system, this incredible network of vessels and pumps and valves, started beating before you were born and will keep beating until the moment you die. It is the most reliable, most continuous, most essential system in your body. And it all starts with the heart. Now we have traced the path of blood from the heart to the tissues and back again. We have seen how the heart creates pressure, how arteries distribute blood, how capillaries exchange oxygen and nutrients, and how veins return blood to the heart. But we have not yet answered one of the most important questions about this entire system. How does the heart know when to beat faster and when to slow down? How does it adjust its output to match the changing needs of your body? The answer lies in a remarkable system of regulation that involves the nervous system, hormones, and local chemical signals. The heart does not just pump at a fixed rate. It constantly adjusts its rate and force of contraction based on what your body is doing. And this regulation happens without any conscious effort on your part. Let us start with the nervous system. The heart is innervated by both branches of the autonomic nervous system, the sympathetic and the parasympathetic. These two systems have opposing effects on the heart. The sympathetic nervous system, often called the fight or flight system, speeds up the heart and increases the force of contraction. The parasympathetic nervous system, often called the rest and digest system, slows the heart down. The sympathetic nerves that supply the heart release a chemical called norepinephrine.
Norepinephrine binds to beta receptors on the heart muscle cells, and this binding triggers a cascade of events that increases the rate of depolarization in the sinoatrial node, speeds up conduction through the atrioventricular node, and increases the force of contraction of the ventricles. The overall effect is to increase cardiac output, to pump more blood to the muscles and organs that need it during times of stress or physical activity. The parasympathetic nerves that supply the heart come from the vagus nerve, the 10th cranial nerve. The vagus nerve releases a chemical called acetylcholine. Acetylcholine binds to muscarinic receptors on the heart, which slows the rate of depolarization in the sinoatrial node and slows conduction through the atrioventricular node. The overall effect is to decrease heart rate and reduce cardiac output, which is appropriate when you are resting, sleeping, or relaxed. The balance between sympathetic and parasympathetic activity is what determines your resting heart rate.
At rest, parasympathetic tone dominates, keeping the heart rate around 70 beats per minute in a typical adult. If you were to block parasympathetic activity, the heart rate would increase to about 100 beats per minute. If you were to remove both sympathetic and parasympathetic input, the heart rate would be determined by the intrinsic firing rate of the sinoatrial node, which is about 100 beats per minute. So your resting heart rate is not just a default setting, it is actively kept lower by constant parasympathetic braking. But the nervous system does not act alone. There are also hormones that affect the heart and blood vessels. The most important of these is epinephrine, also known as adrenaline. Epinephrine is released by the adrenal glands during stress or physical activity.
It travels through the blood and binds to the same beta receptors on the heart that norepinephrine binds to. The effect is the same: increased heart rate, increased conduction speed, and increased force of contraction. Epinephrine also causes vasoconstriction in some blood vessels and vasodilation in others, redistributing blood flow to the muscles and away from the skin and digestive organs. Another important hormone is angiotensin II, which is part of the renin-angiotensin system. This system is activated when blood pressure drops or when the kidneys detect a decrease in blood flow. Angiotensin II is a powerful vasoconstrictor, meaning it narrows blood vessels, which increases blood pressure. It also stimulates the release of aldosterone, a hormone that causes the kidneys to retain sodium and water, increasing blood volume and further raising blood pressure.
And then there is atrial natriuretic peptide, or ANP, which is released by the heart itself when the atria are stretched by increased blood volume. ANP has the opposite effect of angiotensin II. It causes vasodilation and promotes the excretion of sodium and water by the kidneys, reducing blood volume and lowering blood pressure. All of these systems, nervous and hormonal, work together to maintain blood pressure within a narrow range. Blood pressure is not just a passive result of the heart pumping. It is actively regulated by a complex set of reflexes and feedback loops. The most important of these is the baroreceptor reflex. Baroreceptors are specialized nerve endings located in the walls of the carotid arteries and the aorta. They are sensitive to stretch. When blood pressure rises, the arteries stretch and the baroreceptors fire more frequently. This signal travels to the brainstem, specifically to a region called the nucleus tractus solitarius. From there, signals are sent to the sympathetic and parasympathetic centers of the brain. The result is a decrease in sympathetic activity and an increase in parasympathetic activity, which slows the heart and reduces blood pressure. When blood pressure drops, the baroreceptors fire less frequently. This leads to an increase in sympathetic activity and a decrease in parasympathetic activity, which speeds up the heart and raises blood pressure. The baroreceptor reflex is a negative feedback loop, one of the most important regulatory mechanisms in the body. It operates continuously, making small adjustments to keep your blood pressure stable, even as you change position, exert yourself, or experience stress. But the baroreceptor reflex has its limits. It is designed to respond to acute changes in blood pressure, changes that happen over seconds or minutes. It is not very effective at responding to chronic changes, changes that happen over days or weeks. If blood pressure remains elevated for a long time, the baroreceptors reset to a new baseline, and the reflex no longer works to bring pressure back down. This is one reason why high blood pressure or hypertension is so difficult to treat. The body adapts to the elevated pressure and treats it as normal. There are also local mechanisms that regulate blood flow within individual organs. These are not controlled by the nervous system or hormones. They are intrinsic to the tissues themselves. The most important of these is metabolic regulation. When a tissue is active, it consumes more oxygen and produces more waste products like carbon dioxide, hydrogen ions, and adenosine. These substances cause the arterioles in that tissue to dilate, increasing blood flow. This is why your muscles get more blood when you exercise, and why your stomach gets more blood after a meal. Another important local mechanism is myogenic regulation.
This is the response of the smooth muscle in arterioles to changes in pressure. When pressure in an arteriole increases, the smooth muscle contracts, narrowing the vessel. This helps maintain constant blood flow despite changes in perfusion pressure. When pressure decreases, the smooth muscle relaxes, widening the vessel. Myogenic regulation is especially important in the kidneys, where it helps maintain a stable filtration rate. And then there is the endothelium, the inner lining of all blood vessels. The endothelium is not just a passive barrier. It is an active organ that produces substances that regulate vascular tone. The most important of these is nitric oxide, or NO. Nitric oxide is a powerful vasodilator. It is produced by the endothelium in response to various stimuli, including increased blood flow and certain hormones. It diffuses to the underlying smooth muscle and causes it to relax.
This is how blood vessels dilate in response to increased flow, a phenomenon called flow-mediated dilation. The endothelium also produces endothelin, a powerful vasoconstrictor. The balance between nitric oxide and endothelin helps determine vascular tone. In healthy blood vessels, nitric oxide production predominates, keeping vessels dilated. In disease states, such as atherosclerosis or hypertension, nitric oxide production is reduced and vasoconstriction predominates. This contributes to increased vascular resistance and elevated blood pressure. So, let us review what we have learned about the regulation of the cardiovascular system. The nervous system, specifically the autonomic nervous system, provides rapid, moment-to-moment control of heart rate and blood pressure. The sympathetic nervous system speeds up the heart and constricts blood vessels, while the parasympathetic nervous system slows the heart down.
Hormones like epinephrine and angiotensin II provide longer-term regulation, adjusting blood pressure and blood volume over minutes to hours. Local mechanisms, including metabolic and myogenic regulation, adjust blood flow to individual organs based on their needs. And the endothelium produces substances that modulate vascular tone. All of these systems work together in a coordinated fashion. When you stand up, gravity pulls blood into your legs. The baroreceptors detect the drop in pressure in your upper body. The sympathetic nervous system responds by increasing heart rate and constricting veins, which pushes blood back to the heart. This happens within seconds. Without this response, you would feel dizzy or even faint every time you stood up. When you exercise, your muscles produce carbon dioxide and adenosine. These substances dilate the arterioles in your muscles, increasing blood flow.
At the same time, the sympathetic nervous system increases your heart rate and cardiac output. The combination of increased output and decreased resistance in the muscles ensures that your muscles get the oxygen they need. And the arterioles in your skin and digestive organs constrict, redirecting blood away from those areas to the muscles. When you eat a large meal, the arterioles in your stomach and intestines dilate, increasing blood flow to those organs. This is why you might feel sleepy after a big meal. Blood is being redirected to your digestive system, leaving less for your brain and muscles. When you are stressed or frightened, the sympathetic nervous system and the adrenal glands release epinephrine and norepinephrine. Your heart rate increases, your blood pressure rises, and blood is redirected to your muscles, preparing your body to fight or flee.
This is the fight or flight response, and it is a classic example of how the cardiovascular system responds to a perceived threat. All of these responses are automatic. You do not have to think about them. They happen instantly, continuously, and without any conscious effort. Your body is constantly monitoring and adjusting its cardiovascular system, ensuring that every cell gets the oxygen and nutrients it needs. But what happens when this system fails? What happens when the regulatory mechanisms break down? This is where we enter the world of cardiovascular disease, the leading cause of death in the United States and around the world. The most common cardiovascular disease is hypertension, or high blood pressure. Hypertension is defined as a systolic blood pressure of 130 millimeters of mercury or higher, or a diastolic blood pressure of 80 millimeters of mercury or higher. It affects nearly half of all adults in the United States, and it is dangerous because it is often silent. You can have high blood pressure for years and not know it, but over time, high blood pressure damages the arteries. It causes the walls of the arteries to thicken and harden, a process called arteriosclerosis. It increases the workload on the heart, which can lead to heart failure. It damages the kidneys, and it increases the risk of stroke and heart attack. Another common cardiovascular disease is atherosclerosis, the buildup of plaque in the arteries. Plaque is a mixture of fat, cholesterol, calcium, and other substances that accumulates on the inner walls of arteries. Over time, plaque can narrow the arteries, restricting blood flow. If a plaque ruptures, it can cause a blood clot to form, which can block the artery completely. This is what causes a heart attack or a stroke. Heart failure is another major cardiovascular disease. Heart failure does not mean the heart has stopped. It means the heart is not pumping as effectively as it should. Heart failure can be caused by many things, including high blood pressure, heart attacks, infections, and genetic conditions. It results in symptoms such as shortness of breath, fatigue, and swelling in the legs and feet. All of these diseases are consequences of the cardiovascular system's failure to maintain proper regulation and function. Understanding how the system works is the first step in understanding how it can fail. And understanding how it can fail is the first step in developing treatments. In the next chapter, we will explore these diseases in more detail. We will see how high blood pressure damages arteries, how plaque forms and ruptures, and how heart failure develops. We will learn about the treatments that have been developed to manage these conditions, from medications that lower blood pressure to surgical procedures that open blocked arteries. We will see how advances in our understanding of cardiovascular physiology have led to longer, healthier lives. But for now, let us just appreciate the elegance of the system. Your cardiovascular system is a marvel of regulation. It constantly adjusts to your needs, delivering oxygen and nutrients to every cell, removing waste products, and maintaining blood pressure within a narrow range. It does all of this without any conscious effort on your part. It is one of the most sophisticated and reliable systems in the human body. And the next time you feel your heart beating, remember that you are not just feeling a muscle contracting. You are feeling the result of an entire regulatory system working in perfect harmony. You are feeling your body's response to the world around you, constantly adjusting to keep you alive and functioning.
We have spent the last 3 chapters understanding how the heart works, how blood moves through the body, and how the entire system is regulated.
We have traced the path of blood from the heart to the lungs, through the arteries, into the capillaries, back through the veins, and we have seen how the nervous system, hormones, and local signals keep everything in balance. But there is one part of the story we have not yet told. We have talked about the heart as a pump, but we have not talked about how the heart itself stays alive. How does this organ, which pumps blood to every other organ in the body, get its own supply of oxygen and nutrients? This is one of the most fascinating and important questions in all of cardiovascular physiology. Because without its own blood supply, the heart would die within minutes. And if the heart dies, everything else dies. The heart muscle, like any other muscle in your body, needs oxygen and nutrients to function. It cannot survive on the blood that flows through its chambers. The walls of the heart are too thick.
Oxygen cannot diffuse from the blood inside the chambers through the muscle layers. The heart needs its own dedicated network of blood vessels, its own circulatory system within the circulatory system. This is called the coronary circulation. The coronary arteries are the first branches off the aorta. Immediately after blood leaves the left ventricle and passes through the aortic valve, it enters the aorta. And within the first few millimeters of the aorta, 2 small openings give rise to the left and right coronary arteries. These arteries then run along the surface of the heart, dividing into smaller and smaller branches that penetrate deep into the heart muscle. The right coronary artery supplies the right side of the heart, the bottom of the left ventricle, and in many people, the sinoatrial node and the atrioventricular node. The left coronary artery is larger and supplies the left ventricle, the left atrium, and the interventricular septum.
The left coronary artery quickly divides into 2 major branches. The left anterior descending artery, which runs down the front of the heart, and the circumflex artery, which wraps around the back. These arteries are called epicardial arteries because they run along the surface of the heart, just beneath the outer layer. From these epicardial arteries, smaller branches penetrate the muscle, forming a network of arterioles and capillaries that supply every heart muscle cell. The density of capillaries in the heart is among the highest in the body. Every single heart muscle cell is within a few micrometers of a capillary. This ensures that oxygen and nutrients can reach the muscle cells quickly. But here is the critical point. The heart muscle is supplied with blood during a very specific part of the cardiac cycle, and that part is not when you might expect it.
Most organs receive their blood supply during systole, when the heart is contracting and blood is being pushed through the arteries. But the heart is different. The heart muscle is perfused primarily during diastole, when the heart is relaxing. Why is that? The answer has to do with the way the coronary arteries run through the heart muscle. These arteries are not just lying on the surface, they penetrate deep into the muscle. And during systole, when the heart muscle contracts, it squeezes the coronary arteries. The contraction compresses the vessels, especially those that are deep within the thick wall of the left ventricle. This compression is so strong that blood flow through the deep layers of the left ventricle stops completely during systole. So the heart muscle only receives blood during diastole, when the muscle relaxes and the vessels can open. This means that the heart muscle is most vulnerable to inadequate blood flow when the heart rate is very fast. A fast heart rate means shorter diastole, shorter time for the coronary arteries to fill, and less blood reaching the heart muscle. This is one reason why very rapid heart rates can be dangerous. The heart is working harder and faster, but it is getting less blood. The demand for oxygen by the heart muscle is enormous. The heart is one of the most metabolically active organs in the body. At rest, it consumes about 8 to 10% of the body's total oxygen consumption, even though it represents only about 1% of the body's weight. During exercise, the heart's oxygen consumption can increase several times. To meet this demand, the coronary arteries must be able to dilate significantly. The regulation of coronary blood flow is a combination of local, neural, and hormonal factors. The most important of these is local regulation. When the heart muscle is active and consuming more oxygen, it produces metabolites such as adenosine, carbon dioxide, and hydrogen ions.
These substances cause the coronary arterioles to dilate, increasing blood flow. This is an example of metabolic regulation, and it is incredibly efficient. The heart automatically gets more blood when it needs more oxygen. Neural and hormonal factors also play a role. The sympathetic nervous system can cause coronary vasodilation, but its effects are often masked by the powerful local metabolic regulation. In general, the local metabolic response is so strong that it overrides almost everything else. The heart muscle gets the blood it needs based on its own demands. Now, what happens when this supply is compromised? What happens when the coronary arteries are narrowed or blocked? This is the basis of coronary artery disease, the most common cause of death in the United States and around the world. The narrowing of the coronary arteries is usually caused by atherosclerosis, the build-up of plaque in the artery walls. Plaque is a complex mixture of fats, cholesterol, calcium, and cellular debris. It forms over many years, starting with damage to the endothelium, the inner lining of the artery. Over time, plaque accumulates, reducing the diameter of the artery and restricting blood flow. When a coronary artery is narrowed by about 70%, blood flow at rest may still be adequate. But when the heart demands more oxygen during exercise or stress, the narrowed artery cannot deliver enough blood, and the heart muscle becomes ischemic, meaning it does not get enough oxygen. This ischemia causes chest pain, which is called angina pectoris. But the most dangerous event is when a plaque ruptures. A rupture exposes the contents of the plaque to the blood, which triggers the formation of a blood clot. The clot can block the artery completely, cutting off blood flow to a portion of the heart muscle. This is a heart attack, or myocardial infarction. The heart muscle supplied by that artery begins to die within minutes. The longer the blockage lasts, the more muscle is lost. The symptoms of a heart attack include chest pain or discomfort, which may radiate to the arm, neck, or jaw. Shortness of breath, nausea, and sweating are also common. But some heart attacks are silent, producing no symptoms at all. Time is critical during a heart attack. The goal is to restore blood flow as quickly as possible. This can be done with medications that dissolve the clot, or with procedures such as angioplasty, where a catheter is inserted into the blocked artery and a balloon is inflated to open it, often followed by the placement of a stent to keep the artery open. Angioplasty and stenting have revolutionized the treatment of heart attacks. A patient who reaches the hospital within 90 minutes of symptom onset has an excellent chance of surviving with minimal heart damage. But every minute counts. The longer the blood flow is blocked, the more heart muscle dies. And heart muscle does not regenerate. The prevention of coronary artery disease is a major public health priority. The risk factors for atherosclerosis are well known. high blood pressure, high cholesterol, smoking, diabetes, obesity, and a sedentary lifestyle all increase the risk. So do a family history of heart disease and advancing age. Modifiable risk factors can be addressed through lifestyle changes and medications. Statins are a class of drugs that lower cholesterol and have been shown to reduce the risk of heart attacks. They work by inhibiting an enzyme in the liver that produces cholesterol. Blood pressure medications, including ACE inhibitors, beta blockers, and calcium channel blockers, reduce the workload on the heart and lower the risk of heart disease. Aspirin, which inhibits platelet aggregation, can reduce the risk of clot formation.
But even with these treatments, coronary artery disease remains a major cause of death. This is because the disease process begins early in life and progresses over decades. Atherosclerosis is often called a silent disease because people can have significant plaque buildup without any symptoms. In recent years, there has been increasing interest in the prevention of atherosclerosis through lifestyle changes and early detection. The goal is to identify risk factors early and intervene before the disease progresses. This includes regular exercise, a heart-healthy diet, weight management, and smoking cessation. But there is another side to the story of the heart's blood supply. We have talked about what happens when the coronary arteries become blocked. But what about the heart itself? How does it adapt to the demands placed on it? This is the story of cardiac adaptation, of how the heart changes in response to increased workload.
One of the most important adaptations is hypertrophy, an increase in the size of the heart muscle cells. Hypertrophy occurs when the heart is subjected to increased workload, such as during exercise or in the presence of high blood pressure. The heart muscle cells grow larger and produce more contractile proteins. The heart becomes thicker and stronger. But hypertrophy is not always beneficial. There is a difference between physiological hypertrophy, which occurs in response to exercise, and pathological hypertrophy, which occurs in response to disease. Physiological hypertrophy is associated with increased cardiac output and improved performance. Pathological hypertrophy is associated with the development of heart failure. The difference lies in the nature of the stimulus and the resulting changes in the heart muscle. Exercise-induced hypertrophy is accompanied by the growth of new blood vessels and an improvement in the heart's ability to relax and fill.
Disease-induced hypertrophy is often accompanied by fibrosis, the deposition of collagen in the heart muscle, which makes the heart stiff and less able to function effectively. Understanding the mechanisms of hypertrophy and its transition to heart failure is one of the great challenges of modern cardiovascular research. The goal is to develop therapies that promote beneficial hypertrophy and prevent pathological hypertrophy. Another form of cardiac adaptation is remodeling, changes in the shape of the heart after a heart attack. After a heart attack, the surviving heart muscle must take on additional workload. The heart dilates, and the remaining muscle thickens to compensate. This remodeling can be beneficial in the short term, but over time, it can lead to heart failure. The treatments for heart failure have improved dramatically in recent years. Medications such as ACE inhibitors and beta blockers reduce the workload on the heart and improve survival.
For patients with advanced heart failure, cardiac transplantation or mechanical support devices may be life-saving. But the best treatment is prevention. Preventing coronary artery disease prevents heart attacks, and preventing heart attacks prevents the remodeling that leads to heart failure. This is why public health efforts to reduce risk factors are so important. So, to summarize the key points of this chapter,
The heart requires its own blood supply, which is provided by the coronary arteries. These arteries branch off the aorta immediately after it leaves the heart. Blood flow to the heart muscle occurs primarily during diastole. Atherosclerosis of the coronary arteries is the leading cause of death in the United States. A heart attack occurs when a plaque ruptures and a clot blocks a coronary artery. The prevention and treatment of coronary artery disease are major public health priorities.
We have now covered the anatomy, physiology, regulation, and disease of the cardiovascular system. But there is still one more story to tell. The story of how doctors and scientists learn to see inside the beating heart, how they develop the tools and techniques to diagnose and treat heart disease. From the stethoscope to the electrocardiogram, to the cardiac catheterization and the ultrasound, each of these tools has revolutionized our understanding and treatment of heart disease. In the next chapter, we will explore these tools. We will see how a physician can listen to the heart, record its electrical activity, take images of its beating chambers, and even thread a catheter into the coronary arteries. We will see how these diagnostic methods have transformed cardiology from a speculative art into a precise science. And we will understand how the same principles we have been discussing are used every day to save lives. But for now, just think about what we have learned.
The heart, the most remarkable pump in the known universe, must feed itself. It has its own tiny circulatory system, a network of vessels that delivers oxygen and nutrients to its own muscle cells. And when this system fails, the consequences are immediate and devastating. The heart is both the source of life and vulnerable to the same diseases that affect the rest of the body. That is the final piece of the puzzle, the insight that completes our understanding of this incredible organ. We have spent 4 chapters exploring the heart and the circulation. We have traced the path of blood from the heart to the lungs and back through the arteries, the capillaries, and the veins. We have seen how the heart is regulated by the nervous system and hormones. We have seen how the heart feeds itself through the coronary arteries, and we have seen what happens when this system breaks down. But there is still a question we have not fully answered.
How do doctors actually see what is happening inside the heart? How do they listen to its sounds, record its electrical activity, take images of its beating chambers, and even thread catheters into its arteries? The story of how medicine learned to look inside the heart is one of the most fascinating chapters in the history of science, and it is a story that is still being written. For centuries, the only way to examine a heart was to wait until the patient died and then perform an autopsy. A physician could feel the pulse, could listen to the heart sounds by pressing an ear to the chest, could observe the color of the skin and the swelling of the legs. But the heart itself remained invisible. It was a black box, a mysterious organ whose function could only be inferred from its effects on the rest of the body. The first breakthrough came with the stethoscope. In 1816, a French physician named René Laennec was examining a young woman with heart disease. He was uncomfortable pressing his ear directly to her chest, as was the custom at the time. So he rolled a sheet of paper into a cylinder, placed one end on her chest, and listened through the other. To his surprise, the heart sounds were clearer and louder. He had invented the stethoscope. Laennec's monaural stethoscope was a simple wooden tube, but it revolutionized the practice of medicine. For the first time, physicians could listen to the heart without placing their ear directly on the patient's chest. They could hear the characteristic sounds of the cardiac cycle, the lub and the dub of the valves closing. And they could detect abnormal sounds, such as murmurs caused by leaky or narrowed valves.
But the stethoscope could only tell you so much. It could reveal the presence of a murmur, but it could not tell you how severe it was. It could reveal an irregular rhythm, but it could not tell you what was causing it. Physicians needed a way to see the heart's electrical activity. The electrocardiogram, or EKG, was the next great breakthrough. The story begins in the late 19th century, when scientists discovered that the heart generates electrical currents. In 1887, Augustus Waller recorded the first human electrocardiogram using a device called a capillary electrometer. The tracings were poor and difficult to interpret, but they showed that the heart's electrical activity could be measured from the surface of the body. It was Willem Einthoven, a Dutch physiologist, who perfected the electrocardiogram. In 1903, Einthoven published a paper describing his string galvanometer, a device that could record the heart's electrical activity with remarkable precision. He assigned the letters P, Q, R, S, and T to the various waves of the electrocardiogram, a convention we still use today. Einthoven's electrocardiogram was a bulky instrument that required a large room and a team of technicians to operate. But it worked. It could detect arrhythmias, conduction abnormalities, and signs of heart damage. It could even help diagnose a heart attack. Einthoven was awarded the Nobel Prize in Physiology or Medicine in 1924 for his work. Today, the electrocardiogram is one of the most common and important diagnostic tests in medicine. A simple EKG can be performed in a doctor's office in just a few minutes, using a small device that records the heart's electrical activity through electrodes placed on the skin. It can detect arrhythmias, such as atrial fibrillation or ventricular tachycardia. It can detect evidence of a previous heart attack, such as Q waves or ST segment changes. And it can help diagnose conditions such as pericarditis or pulmonary embolism. But the EKG has its limitations. It can detect electrical activity, but it cannot show the structure of the heart. It cannot show the size of the chambers, the thickness of the walls, or the movement of the valves. To see those things, physicians needed another tool. The next breakthrough came with the development of echocardiography. Echocardiography, or cardiac ultrasound, uses high-frequency sound waves to create images of the heart. The principle is similar to sonar, the technology used to detect submarines. Sound waves are sent into the body, and the echoes that bounce back are used to create an image. The first echocardiograms were performed in the 1950s. The early devices were crude, but they could detect the movement of the heart valves and the walls of the chambers. Over the following decades, echocardiography improved dramatically. The images became clearer, the resolution became higher, and the devices became smaller and more portable. Today, echocardiography is one of the most important diagnostic tools in cardiology. A two-dimensional echocardiogram can show the heart in real time, beating in its natural rhythm.
It can measure the size of the chambers and the thickness of the walls. It can assess the function of the heart valves, detecting stenosis, the narrowing of the valve, or regurgitation, the leakage of blood backward through the valve. It can measure the ejection fraction, the percentage of blood that is pumped out of the left ventricle with each beat. And it can detect pericardial effusion, the accumulation of fluid around the heart. There are several types of echocardiograms. A transthoracic echocardiogram is performed by placing the probe on the chest wall. A transesophageal echocardiogram involves inserting a probe into the esophagus, which lies directly behind the heart, providing higher resolution images. A stress echocardiogram is performed during exercise or with a medication that increases the heart rate. to assess how the heart responds to stress. Echocardiography is a remarkable tool because it is non-invasive. It does not require needles, catheters, or radiation.
It can be performed quickly and safely, even on the most critically ill patients, and it provides information that would otherwise require more invasive procedures. But even echocardiography has limitations. It cannot see the coronary arteries. It cannot assess the severity of coronary artery disease. To see the coronary arteries, physicians needed another tool. The next breakthrough was cardiac catheterization. Cardiac catheterization involves threading a thin, flexible tube called a catheter through a blood vessel, usually in the groin or wrist, and advancing it into the heart. The catheter can be used to measure pressures, inject contrast dye, and perform other procedures. The history of cardiac catheterization begins with Werner Forssmann, a young German physician who, in 1929, performed the first cardiac catheterization on himself.
Forssmann anesthetized his own arm, inserted a catheter into his antecubital vein, and advanced it all the way into his right atrium. He then walked to the X-ray department and had an image taken to confirm his success. He was fired from his job for the stunt, but he eventually won the Nobel Prize in 1956. Cardiac catheterization remained a risky and experimental procedure for many years, but in the 1950s and 60s, it became a routine diagnostic tool. Physicians could now measure the pressure inside the heart chambers, assess the function of the valves, and take blood samples from the various chambers to measure oxygen saturation. But the most important application of cardiac catheterization was coronary angiography. Coronary angiography involves injecting contrast dye into the coronary arteries and taking X-ray images. The dye makes the arteries visible, allowing the physician to see any areas of narrowing or blockage.
Coronary angiography was first performed in 1958 by a cardiologist named Mason Soanes. Soanes was examining a patient and inadvertently injected contrast dye into the right coronary artery. Instead of causing the expected complication, the dye briefly appeared on the X-ray screen. Soanes realized that he had discovered a way to visualize the coronary arteries. Today, coronary angiography is the gold standard for diagnosing coronary artery disease. It can identify the location and severity of arterial blockages. It can guide decisions about treatment, such as whether to perform angioplasty and stenting or coronary artery bypass surgery. And it can be used to monitor the progression of the disease. But coronary angiography is an invasive procedure. It carries a small but real risk of complications, including bleeding, infection, kidney damage, and stroke. And it can only show the anatomy of the arteries, not the function of the heart muscle.
That is where other imaging techniques come in. Nuclear imaging, such as single-photon emission computed tomography, or SPECT, or positron emission tomography, or PET, can assess the function of the heart muscle. These techniques use radioactive traces that are taken up by the heart muscle. Areas of the heart that are receiving adequate blood flow take up the tracer. Areas that are not appear as dark spots on the image. This can identify areas of the heart that are at risk of infarction. Cardiac magnetic resonance imaging, or MRI, is another powerful tool. MRI uses a magnetic field and radio waves to create highly detailed images of the heart. It can assess the structure, function, and tissue composition of the heart. It can detect areas of scar tissue following a heart attack. It can even measure the myocardial perfusion, the blood flow to the heart muscle, at rest and during stress. Cardiac computed tomography, or CT,
is a third advanced imaging technique. CT uses X-rays and computer processing to create three-dimensional images of the heart. It can visualize the coronary arteries and detect calcified plaque. It can even perform coronary CT angiography, which provides images of the coronary arteries similar to traditional angiography, but without the need for a catheter. All of these tools, the stethoscope, the electrocardiogram, the echocardiogram, cardiac catheterization, nuclear imaging, MRI, and CT, are part of the modern cardiologist's armamentarium. Each tool provides a piece of information, and the combination of these pieces gives a complete picture of the heart. But the goal of all this imaging is not just to see the heart, it is to guide treatment. If a patient has angina, chest pain caused by inadequate blood flow, an echocardiogram can assess the heart's function. An EKG can detect electrical abnormalities, and a coronary angiogram can identify the location of blockages. If the blockages are severe, the patient may be a candidate for angioplasty or bypass surgery. If the blockages are mild, lifestyle changes and medications may be sufficient. The development of these diagnostic tools is one of the great success stories of modern medicine. It has transformed the care of patients with heart disease. It has led to earlier diagnosis, more targeted treatments, and better outcomes. But there is still much work to be done. Heart disease remains the leading cause of death in the United States, and the tools we have described are only as good as the clinicians who use them and the patients who benefit from them. The goal of all this technology is to see the heart, to understand its function and its diseases, and to guide treatment. And the story of how we learn to see the heart is a testament to human curiosity and ingenuity. It is a story of doctors and scientists who are willing to try new things, take risks, and challenge the assumptions of their time. In the next chapter, we will look to the future. We will see how advances in genetics, molecular biology, and artificial intelligence are transforming the field of cardiology. We will see how stem cells might be used to repair damaged heart muscle, how gene therapy might be used to treat inherited heart diseases, and how wearable devices might be used to monitor heart health in real time. But for now, let us just appreciate the journey we have taken. From the stethoscope to the cardiac MRI, from a simple wooden tube to a sophisticated imaging machine, we have seen how medicine has learned to look inside the heart. And in the process, we have gained a deeper understanding of this remarkable organ. The next time you see a doctor with a stethoscope, or a nurse placing electrodes on your chest, or a technician performing an echocardiogram, remember that you are witnessing the results of centuries of discovery. You are being cared for by the accumulated wisdom of generations of physicians and scientists who were dedicated to understanding the heart. And that understanding continues to grow every single day. We have spent 5 chapters exploring the heart and the circulation. We have traced the path of blood from the heart to the lungs and back, through the arteries, the capillaries, and the veins. We have seen how the heart is regulated by the nervous system and hormones. We have seen how the heart feeds itself through the coronary arteries. We have seen what happens when this system breaks down, and we have seen how doctors use a variety of tools to see inside the heart. Now it is time to look to the future. What will the next 50 years bring? How will our understanding of the heart and circulation continue to evolve? And how will these advances change the way we treat heart disease? The future of cardiology is being shaped by several powerful forces. Advances in genetics and molecular biology are revealing the genetic basis of heart disease. Advances in materials science and engineering are leading to new devices and treatments.
and advances in data science and artificial intelligence are enabling new ways of analyzing and interpreting information. Let us start with genetics. Over the past 2 decades, scientists have identified dozens of genes that increase the risk of heart disease. These genes affect cholesterol metabolism, blood pressure regulation, inflammation, and many other pathways. Understanding these genes is leading to new therapies that target specific pathways. One of the most exciting developments is the use of gene editing to treat inherited heart diseases. Gene editing technologies, such as CRISPR, allow scientists to precisely modify DNA. In the future, it may be possible to correct the genetic mutations that cause diseases such as hypertrophic cardiomyopathy, long QT syndrome, and familial hypercholesterolemia. These are diseases that affect thousands of people and can cause sudden death at a young age. Stem cell therapy is another area of active research. Stem cells are undifferentiated cells that can develop into different types of cells. Scientists are exploring the use of stem cells to repair damaged heart muscle after a heart attack. The idea is to inject stem cells into the heart, where they could potentially differentiate into new heart muscle cells and restore function. While early clinical trials have shown mixed results, the research is ongoing and holds promise. Tissue engineering is a related field.
Scientists are growing heart tissue in the laboratory, using scaffolds to create 3-dimensional structures that resemble the heart. These engineered tissues could eventually be used to patch damaged areas of the heart, or even to create whole organs for transplantation. Another area of research is the use of biomaterials to deliver drugs and growth factors directly to the heart. Scientists are developing nanoparticles and other delivery systems that can target the heart specifically, reducing the side effects of systemic drug therapy. Now let us talk about devices. The field of cardiovascular devices has advanced dramatically over the past few decades. Pacemakers, implantable defibrillators, and ventricular assist devices have become smaller, more reliable, and more sophisticated. The latest generation of these devices can communicate wirelessly with monitoring systems, allowing physicians to track a patient's heart rhythm and device function remotely.
One of the most exciting developments is the artificial heart. The total artificial heart, a device that replaces the entire heart, has been implanted in a small number of patients. While the early devices were bulky and had limited durability, newer designs are smaller, more efficient, and more durable. The goal is to create a device that can replace a failing heart for years or even decades. Another area of rapid progress is in cardiac imaging. The imaging tools we discussed in the last chapter continue to improve. Higher resolution, faster scanning times, and more sophisticated image processing are enabling more accurate diagnosis and better treatment planning. Artificial intelligence is also transforming cardiology. AI algorithms can analyze large datasets of medical images and identify patterns that may be missed by human observers. These algorithms can help detect abnormalities on echocardiograms, CT scans, and MRI scans. They can also predict outcomes, such as the risk of a heart attack or the likelihood of response to treatment. AI is also being used to analyze wearable device data. Millions of people now wear smartwatches and fitness trackers that can monitor heart rate, physical activity, and even detect atrial fibrillation. This data is being used to identify individuals at risk and to track the effectiveness of treatments. But perhaps the most important area of progress is in prevention. The future of cardiology is not just about treating heart disease, it is about preventing it. And this requires a shift in focus from the individual to the population. We already know the major risk factors for heart disease:
high blood pressure, high cholesterol, smoking, diabetes, obesity, and physical inactivity. We know how to reduce these risk factors through lifestyle changes and medications, but we have not been successful at implementing these measures at a population level.
The challenge is to change behaviors, to encourage people to eat healthier, exercise more, and stop smoking, to make healthy choices the easy choices. This requires public health interventions, policy changes, and education. It also requires addressing the social determinants of health, the conditions in which people are born, grow, live, work, and age. People with lower socio-economic status have higher rates of heart disease. This is not just a matter of access to healthcare. It is about the environments in which people live, the stress they experience, the food they have access to, and the opportunities they have for physical activity. Addressing these social determinants will require a coordinated effort across multiple sectors: healthcare, education, housing, transportation, and urban planning. It is a complex challenge, but it is one that we must meet if we are to reduce the burden of heart disease. Now, let us look at some of the more futuristic areas of research. One area is the use of nanotechnology to deliver drugs to the heart. Nanoparticles are tiny particles that can be engineered to carry drugs and target specific tissues. In the future, it may be possible to use nanoparticles to deliver drugs directly to the heart muscle, reducing the side effects of systemic drug therapy. Another area is the use of the microbiome, the collection of bacteria and other microorganisms that live in our bodies. The microbiome has been linked to many diseases, including heart disease. Understanding how the microbiome affects the heart and blood vessels could lead to new therapies that target the microbiome. And then there is the field of synthetic biology. Synthetic biology involves designing and constructing new biological systems. In the future, scientists may be able to engineer cells that can produce therapeutic molecules, such as growth factors or hormones, in response to specific signals. These engineered cells could be implanted in the heart or elsewhere to treat disease. All of these advances are exciting, but they also raise important ethical and social questions. Should we use gene editing to prevent heart disease? Who should have access to these technologies? How should we balance the benefits and risks? These are questions that will need to be addressed as the technology advances. But perhaps the most important message of all is that the future of cardiology is not just about technology, it is about people. It is about understanding the heart and the circulation in all their complexity, and using that understanding to improve the lives of patients. It is about treating the whole person, not just the disease. So, let us review what we have covered in this chapter. The future of cardiology is being shaped by genetics, molecular biology, materials science, engineering, data science, and artificial intelligence. New therapies, devices, and diagnostic tools are being developed, and there is a growing emphasis on prevention and addressing the social determinants of health. But even as we look to the future, we must remember the lessons of the past. The heart is a remarkable organ, the most reliable pump in the known universe. It has been beating without interruption for your entire life. It will continue to beat until the moment you die. And it is this very reliability, this constancy, that makes it so essential to life. We have come a long way since the ancient Egyptians believed the heart was the seat of the soul. We have learned so much about the structure, function, and regulation of the heart and circulation. We have developed tools to see inside the heart, to diagnose its diseases, and to treat its failures. And yet, there is still so much we do not know. The heart remains one of the most complex and mysterious organs in the body. It is a pump, yes,
but it is also a sensory organ, a hormonal organ, and a rhythm generator. It is influenced by the brain, by the immune system, and by the environment. It is a miracle of nature, a testament to the power of evolution. So, as you lie there tonight, listening to the sound of your own heart, think about everything you have learned. Think about the 4 chambers and the 4 valves. Think about the coronary arteries and the conduction system. Think about the regulation of blood pressure and the exchange of oxygen and nutrients in the capillaries. Think about the journey of a single red blood cell, from the left ventricle, through the aorta, through the arteries and arterioles, into the capillaries, back through the venules and veins, and into the right atrium. Think about the millions of such journeys that happen every single minute of every single day. And think about the future, the advances that are being made right now in laboratories and clinics around the world that will one day transform the treatment of heart disease, the therapies that will be developed, the devices that will be invented, the knowledge that will be gained. Because the story of the heart is not finished. It is still being written. And we are all part of that story. We have traveled a long way together through the story of the heart. We have explored its anatomy, its physiology, its regulation, its diseases, the tools we use to diagnose it, and the future of cardiology. But there is one more dimension to this story that we have not yet fully explored. One more aspect of the heart that makes it truly remarkable. And that is its development. How does the heart form? How does a simple tube of cells transform into the complex 4-chambered pump that beats inside your chest? And how does this development, the process that begins just 3 weeks after conception, shape the heart you have today? The story of the developing heart is one of the most beautiful and complex stories in all of biology. It is a story of genetic programs, cellular migrations, and intricate folding and remodeling. It is a story that begins before you even know you are pregnant and continues until the moment you are born. Let us start at the beginning. The human heart is the first organ to form and the first to function. It begins to beat at about 3 weeks after conception. At that time, the embryo is just a tiny disc of cells, barely visible to the naked eye. But already a pair of primitive tubes have formed, and they are beginning to fuse into a single tube that will become the heart. This early heart is a simple, straight tube. It has no chambers, no valves, no separate circulations. It is just a muscular tube that contracts rhythmically, pushing blood in one direction.
But over the next few weeks, this simple tube will undergo a remarkable transformation. The tube begins to loop. One end bends to the right, the other to the left, forming a C-shaped loop. This looping is the first step in creating the 4 chambers of the heart. The looping heart then begins to divide internally. Septa, or walls, begin to form, separating the atria from each other and the ventricles from each other. The separation of the atria and ventricles is a complex process. It involves the formation of several septa, which grow from different directions and eventually fuse. It also involves the formation of the valves, which develop from endocardial cushions, specialized swellings of tissue. The formation of the ventricles is equally complex. The ventricles develop from 2 different regions of the primitive heart tube.
The left ventricle forms from the primitive ventricle, while the right ventricle forms from the bulbus cordis, a region that is initially located to the right of the primitive ventricle. The development of the conduction system is also fascinating. The sinoatrial node, the atrioventricular node, and the bundle of His all develop from specialized cells that acquire the ability to generate or conduct electrical impulses. This process is regulated by a complex network of genes that specify the fate of these cells. The development of the coronary arteries is another remarkable story. The coronary arteries develop from the epicardium, the outer layer of the heart. Cells from the epicardium migrate into the heart muscle and form the endothelial cells that line the coronary vessels. The smooth muscle cells of the coronary arteries develop from the neural crest, a group of cells that also contribute to the formation of the autonomic nervous system.
And then, of course, there is the development of the great vessels. The aorta, the pulmonary artery, and the vena cava all develop from the primitive aortic arches and related structures. The remodeling of these structures is a delicate ballet, a process that must occur perfectly to ensure normal blood flow. Now, what happens when this development goes wrong? The result is a congenital heart defect, a structural abnormality of the heart or great vessels that is present at birth. Congenital heart defects are the most common type of birth defect, affecting about 1 in every 100 babies. There are many types of congenital heart defects. Some are simple, such as a small hole between the atria, called an atrial septal defect, or between the ventricles, called a ventricular septal defect. Others are more complex, such as tetralogy of Fallot, a combination of 4 abnormalities that severely impairs blood flow to the lungs. The causes of congenital heart defects are varied.
Some are genetic, caused by mutations in specific genes.
Others are environmental, caused by exposure to certain drugs or infections during pregnancy. In many cases, the cause is unknown. The treatment of congenital heart defects has advanced dramatically over the past several decades. Many defects can now be repaired with surgery or catheter-based procedures. Children born with even the most complex defects can now survive to adulthood and live relatively normal lives. But the story of the developing heart is not just about birth defects. It is also about the heart's ability to adapt after birth. The transition from fetal to neonatal circulation is a critical period. In the fetus, the heart is pumping blood through the placenta, not the lungs. After birth, the lungs must take over the function of gas exchange, and the heart must adapt to this new role. The transition involves closure of several fetal structures.
The foramen ovale, a hole between the atria that allows blood to bypass the lungs, closes soon after birth. The ductus arteriosus, a blood vessel that connects the pulmonary artery to the aorta, also closes. These closures redirect blood flow from the placenta to the lungs, ensuring that the newborn receives oxygenated blood. The postnatal heart continues to grow and develop. The heart muscle cells, or cardiomyocytes, continue to divide for a short time after birth. But by early childhood, the heart muscle cells lose their ability to divide. This is why a heart attack is so damaging. The heart muscle cannot regenerate. But the heart can adapt to increased demands. The heart muscle cells can grow larger, a process called hypertrophy. The heart can also form new blood vessels, a process called angiogenesis. These adaptations allow the heart to respond to conditions such as exercise or high blood pressure. However, there is a limit to this adaptability. If the demands on the heart are too great, the heart can fail. This is the basis of heart failure, a condition in which the heart cannot pump enough blood to meet the needs of the body.
Now, let us connect this back to the overall story of the cardiovascular system. The development of the heart is a blueprint for understanding its structure and function. The heart's anatomy is a result of its developmental history. The chambers, the valves, the conduction system, and the coronary arteries are all products of a complex developmental process. And understanding this development is not just an academic exercise. It has practical implications. Understanding how the heart develops can help us understand why certain diseases occur. For example, understanding the development of the coronary arteries can help us understand why they are susceptible to atherosclerosis. Understanding development can also help us develop new therapies.
If we can understand the signals that guide the development of the heart, we might be able to use those signals to repair damaged hearts. This is the goal of regenerative medicine, a field that is still in its early stages but holds great promise. So, what have we learned in this chapter? The heart develops from a simple tube into a complex four-chambered pump. This process is regulated by a complex network of genes and cellular interactions. When development goes wrong, the result is a congenital heart defect. The transition from fetal to neonatal circulation is a critical period, and the heart continues to grow and adapt after birth. We have covered a lot of ground in this series. We started with the basic anatomy of the heart and circulation. We traced the path of blood through the body. We explored the regulation of the cardiovascular system by the nervous system and hormones. We examined the coronary circulation and the diseases that affect it.
We looked at the tools doctors use to diagnose heart disease. We looked to the future of cardiology. And we have explored the development of the heart. But there is one more chapter to write, one more dimension to the story of the heart. And that is the story of the heart in health and disease. How does the heart work when it is healthy? And what happens when it fails? We have touched on many of these topics throughout the series, but in the final chapter, we will bring everything together. We will see how the anatomy, physiology, regulation, disease, diagnosis, and treatment of the heart all fit together. We will see how the heart, the most remarkable pump in the known universe, sustains life from the first beat to the last. So, let us continue this journey together. Let us explore the heart in all its complexity and wonder. And let us appreciate the miracle that beats inside your chest every second of every day. We have spent 7 chapters exploring the heart from every angle.
We have traced its anatomy, its physiology, its regulation, its diseases, the tools we use to diagnose it, the future of cardiology, and its development from a simple tube of cells into the complex pump it is today. But there is one more chapter to write, one more dimension to the story, and that is the story of the heart in health and disease, seen as a single continuous narrative. Because the heart is not just a collection of parts. It is not just a pump, or an electrical system, or a network of vessels. It is a living organ, a dynamic system that adapts to the demands placed on it. And understanding how it works in health is the key to understanding what goes wrong in disease. Let us start with a healthy heart. What does it look like? What does it feel like? And how does it function? A healthy heart is a muscular organ, about the size of your fist, weighing less than a pound. It sits in the chest, slightly left of center, nestled between the lungs. It is enclosed in a protective sac called the pericardium, which contains a small amount of fluid to reduce friction. The heart beats rhythmically, about 60 to 100 times per minute at rest. Each beat is a coordinated sequence of electrical and mechanical events. The electrical signal starts in the sinoatrial node, spreads through the atria, delays briefly at the atrioventricular node, and then spreads through the ventricles, causing them to contract. The mechanical event is the contraction of the heart muscle, which ejects blood into the pulmonary artery
and the aorta. A healthy heart pumps about 5 quarts of blood per minute at rest. During exercise, this can increase to more than 8 gallons per minute. The heart can adapt to changes in demand, increasing its rate and force of contraction in response to physical activity, stress, or illness. A healthy heart has normal blood pressure.
The systolic pressure, the pressure during contraction, is less than 120 millimeters of mercury. The diastolic pressure, the pressure during relaxation, is less than 80 millimeters of mercury. Normal blood pressure ensures that blood flows to all organs without damaging the blood vessels. A healthy heart has normal coronary arteries. The arteries are open and free of plaque. Blood flows freely to the heart muscle, providing the oxygen and nutrients it needs to function. A healthy heart has normal valves. The valves open and close smoothly, allowing blood to flow in one direction. There are no leaks, no stenosis, no murmurs. A healthy heart has a normal rhythm. The heart rate is regular, with no skipped beats, no extra beats, no dangerous arrhythmias. A healthy heart is a marvel of engineering. It is a pump that works continuously for decades without failure. It is a testament to the power of natural selection, to the elegance of biological design.
But the heart is not invincible. It is vulnerable to disease, to injury, to wear and tear. And when the heart fails, the consequences are immediate and devastating. Heart disease is the leading cause of death in the United States and around the world. It encompasses a wide range of conditions, from coronary artery disease to heart failure, to arrhythmias, to valvular disease. Each of these conditions has a different cause, a different mechanism, a different treatment. Coronary artery disease is the most common type of heart disease. It is caused by atherosclerosis, the buildup of plaque in the coronary arteries. The plaque narrows the arteries, reducing blood flow to the heart muscle. When the demand for oxygen exceeds the supply, the result is ischemia, which causes chest pain, or angina. When a plaque ruptures and a clot forms, the result is a heart attack. Heart failure is another common type of heart disease. Heart failure occurs when the heart cannot pump enough blood to meet the needs of the body. This can be caused by damage to the heart muscle, such as from a heart attack, or by conditions that increase the workload of the heart, such as high blood pressure. Heart failure is a chronic condition that requires ongoing management. Arrhythmias are disorders of the heart's rhythm. They can be caused by problems with the conduction system, by damage to the heart muscle, or by other conditions. Some arrhythmias are harmless, others are life-threatening. The most dangerous arrhythmia is ventricular fibrillation, a chaotic rhythm that can cause sudden death. Valvular disease is another type of heart disease. The valves can become narrowed or stenotic, or they can become leaky or regurgitant. Valvular disease can be caused by congenital defects, by infections, or by degenerative changes. The treatment may involve medication or surgical repair or replacement. Now, let us think about how these diseases develop. They do not develop overnight. They develop over years, often decades. They are the result of a complex interaction between genetics, lifestyle, and environment. Genetics plays a role in many types of heart disease. There are genes that increase the risk of high blood pressure, high cholesterol, and coronary artery disease. There are genes that cause inherited forms of heart failure and arrhythmias. Understanding these genetic factors can help identify individuals at risk and guide treatment. Lifestyle also plays a role. Diet, exercise, smoking, and stress all affect the heart. A diet high in saturated fat and cholesterol increases the risk of atherosclerosis. Physical inactivity increases the risk of obesity, diabetes, and high blood pressure. Smoking damages the blood vessels and increases the risk of heart attack. Chronic stress can raise blood pressure and increase the risk of arrhythmias. Environment also matters.
Air pollution, noise pollution, and exposure to certain chemicals can increase the risk of heart disease. The social environment, including income, education, and access to healthcare, also affects heart health. The good news is that many types of heart disease are preventable. By addressing the risk factors, we can reduce the incidence of heart disease. This means eating a healthy diet, exercising regularly, not smoking, managing stress, and controlling blood pressure and cholesterol. The treatment of heart disease has advanced dramatically over the past several decades. There are now effective medications for most types of heart disease. There are procedures, such as angioplasty and stenting, that can open blocked arteries. There are surgeries, such as bypass surgery and valve replacement, that can repair damaged hearts. And there are devices, such as pacemakers and defibrillators, that can regulate the heart's rhythm. But the best treatment is prevention.
Preventing heart disease is better than treating it. This is why public health efforts to reduce risk factors are so important. This is why we need to create environments that make healthy choices easier. Now, let us bring everything together. The heart is a remarkable organ. It is a pump that works continuously for decades. It is a system that adapts to the demands placed on it. It is regulated by the nervous system, by hormones, and by local signals. It has its own blood supply, provided by the coronary arteries. It can be affected by disease, but it can also be treated. We have covered a lot of ground in this series. We have traced the path of blood from the heart to the lungs and back. We have explored the regulation of the cardiovascular system. We have examined the coronary circulation and the diseases that affect it. We have looked at the tools doctors use to diagnose heart disease. We have looked to the future of cardiology. We have explored the development of the heart. And we have seen the heart in health and disease. But there is one more aspect of the heart that we have not yet fully explored. One more dimension that makes the heart truly remarkable. And that is its ability to heal. The heart has a limited ability to heal itself. After a heart attack, the damaged heart muscle is replaced by scar tissue. Scar tissue does not contract, and it does not conduct electricity, so the heart loses function. But the heart can adapt. The surviving heart muscle can work harder. The heart can remodel, changing its shape to compensate for the loss of function, and new blood vessels can form, improving blood flow to the surviving muscle. And there is research that suggests the heart has more regenerative capacity than we once thought. Scientists have found that the heart can generate new cardiomyocytes, albeit at a very slow rate. This finding has opened up new avenues of research.
If we can find ways to stimulate the heart to regenerate, we might be able to repair damaged hearts. This is a goal of regenerative medicine, and it is one of the most exciting areas of cardiovascular research. If we can harness the heart's own regenerative capacity, we might be able to treat heart disease in a completely new way. So, let us review what we have learned in this chapter. A healthy heart is a marvel of engineering. It works continuously for decades without failure. But the heart is vulnerable to disease. The most common types of heart disease are coronary artery disease, heart failure, arrhythmias, and valvular disease. These diseases develop over years, often decades, and are influenced by genetics, lifestyle, and environment. The treatment of heart disease has advanced dramatically, but prevention remains the best approach. And the heart has a limited ability to heal itself. But research is ongoing to find ways to enhance this ability.
We have now completed our journey through the heart. We have explored its anatomy, its physiology, its regulation, its diseases, the tools we use to diagnose it, the future of cardiology, its development, and its ability to heal. We have seen the heart in health and disease. We have traced its path from a simple tube of cells to the complex 4-chambered pump it is today. The heart is a remarkable organ. It is the most reliable pump in the known universe. It works continuously for decades without failure. It adapts to the demands placed on it. It is regulated by a complex network of signals. It has its own blood supply. It can be affected by disease, but it can also be treated. And it has a limited ability to heal itself. The heart is also a symbol of life, of love, of courage. It is the organ that we associate with our deepest emotions. When we say heart, we mean something more than just a pump. We mean the essence of who we are. So, as you lie there tonight, listening to the sound of your own heart, think about everything you have learned. Think about the 4 chambers and the 4 valves. Think about the coronary arteries and the conduction system. Think about the regulation of blood pressure and the exchange of oxygen and nutrients in the capillaries. Think about the journey of a single red blood cell, from the left ventricle, through the aorta, through the arteries and arterioles, into the capillaries, back through the venules and veins, and into the right atrium. Think about the millions of such journeys that happen every single minute of every single day. Think about the fact that your heart has been beating without interruption since before you were born. Think about the fact that it will continue to beat until the moment you die. And remember that you are the heart, not just the muscle, but the life that it sustains. You are the reason it beats. You are the reason it never stops.
And that is something worth thinking about as you settle in tonight. We have now covered the heart from its earliest development to its function in health and disease. We have traced the path of blood, understood the electrical system, explored the coronary circulation, and seen how modern medicine diagnoses and treats heart conditions. But there is one more aspect of this story that deserves our attention. One more layer of understanding that connects everything we have learned. And that is the physics of the heart. The principles of pressure, flow, and resistance that govern how blood moves through the body. Because the heart is not just a biological organ. It is a physical pump. And like any pump, it operates according to the laws of physics. Understanding these laws is essential for understanding how the heart works, how it can fail, and how we can treat it. Let us start with pressure. Pressure is the force exerted by a fluid against the walls of its container. In the cardiovascular system, the fluid is blood, and the container is the blood vessels. The heart creates pressure by contracting and squeezing blood into the arteries. This pressure is what drives blood flow through the circulation. The pressure in the arteries is highest during systole, when the heart contracts and ejects blood. This is called the systolic pressure. In a healthy adult, the systolic pressure is about 120 millimeters of mercury. The pressure in the arteries is lowest during diastole, when the heart relaxes and fills with blood. This is called the diastolic pressure, and it is about 80 millimeters of mercury. The difference between the systolic and diastolic pressure is called the pulse pressure, and it is about 40 millimeters of mercury. Now, let us think about what these numbers mean. A pressure of 120 millimeters of mercury means that the pressure in the arteries is sufficient to push a column of mercury 120 millimeters high. Mercury is a dense liquid, about 13.5 times denser than water. So 120 millimeters of mercury is equivalent to about 5.5 feet of water. That is a lot of pressure. The heart generates this pressure by contracting its muscular walls. The left ventricle, which pumps blood to the entire body, has the thickest walls and generates the highest pressure. The right ventricle, which pumps blood only to the lungs, has thinner walls and generates lower pressure. This difference in pressure is appropriate for the different demands of the two circulations. Now, let us talk about flow. Flow is the volume of blood that passes through a given point in the circulation per unit of time. The total flow is called cardiac output, and it is about 5 quarts per minute at rest.
Cardiac output is determined by 2 factors: heart rate, the number of beats per minute, and stroke volume, the volume of blood ejected with each beat. The product of heart rate and stroke volume is cardiac output. Flow is directly proportional to pressure. This means that if the pressure increases, the flow increases, assuming the resistance remains constant. And if the pressure decreases, the flow decreases. This relationship is described by a simple equation. Flow equals pressure divided by resistance. This is known as Poiseuille's law, named after Jean Poiseuille, a French physician and physicist who studied the flow of fluids through tubes. Resistance is the opposition to flow. In the cardiovascular system, resistance is determined by the diameter of the blood vessels. The smaller the vessel, the greater the resistance. The arterioles are the main site of resistance in the circulation.
By constricting or dilating, the arterioles can change the resistance and therefore change the flow. The relationship between flow, pressure, and resistance is fundamental to understanding the cardiovascular system. If the pressure remains constant and the resistance increases, the flow decreases. If the resistance remains constant and the pressure increases, the flow increases. And if the flow remains constant and the resistance increases, the pressure increases. This relationship explains many aspects of cardiovascular physiology. For example, when you exercise, your muscles need more blood. The arterioles in the muscles dilate, decreasing resistance and increasing flow. At the same time, your heart rate and stroke volume increase, increasing cardiac output and pressure. The result is that your muscles get the blood they need. When you have high blood pressure, the resistance in the arterioles is increased.
This means that the heart has to work harder to push blood through the narrowed vessels. Over time, this increased workload can lead to hypertrophy of the heart muscle and eventually to heart failure. Now, let us talk about the properties of the blood vessels. The arteries are thick-walled vessels that can withstand high pressure. Their walls contain elastic fibers that allow them to stretch and recoil. This elasticity is important because it helps to maintain blood flow during diastole. When the heart contracts, the arteries stretch, absorbing some of the pressure. When the heart relaxes, the arteries recoil, pushing blood forward. This is why the blood flow in the arteries is continuous, even though the heart beats intermittently. The arterioles are the resistance vessels. They have thick walls of smooth muscle that can contract or relax, changing their diameter. This allows them to regulate blood flow to different organs.
For example, during digestion, the arterioles in the gastrointestinal tract dilate, increasing blood flow to the digestive organs. During exercise, the arterioles in the muscles dilate,
increasing blood flow to the muscles. And during cold exposure, the arterioles in the skin constrict, reducing blood flow to the skin and conserving heat. The capillaries are the exchange vessels. They have very thin walls, only 1 cell thick, that allow oxygen and nutrients to diffuse out of the blood and into the tissues, and carbon dioxide and waste products to diffuse from the tissues into the blood. The capillaries are so small that red blood cells have to pass through them single file, and their total surface area is enormous, about the size of a tennis court. The veins are the capacitance vessels. They are thin-walled and distensible, meaning they can hold a large volume of blood at low pressure. About 2/3 of the blood in the body is in the veins at any given time.
The veins serve as a reservoir for blood. When the body needs more blood, such as during exercise, the veins constrict, pushing blood back to the heart. Now, let us talk about the physics of the heart itself. The heart is a muscle, and like all muscles, it generates force by contracting. The force generated by the heart is determined by the length of the muscle fibers at the beginning of contraction. This is known as the Frank-Starling law. According to this law, the more the heart is filled with blood, the more it stretches, and the more forcefully it contracts. This is a mechanism that allows the heart to match its output to its input. If more blood returns to the heart contracts more forcefully and pumps more blood. The Frank-Starling law is one of the most important principles of cardiac physiology. It ensures that the heart pumps all the blood that returns to it. If the venous return increases, the heart pumps more blood. If the venous return decreases, the heart pumps less blood. This is why the heart does not need a complex control system to match its output to its input. It simply responds to the amount of blood it receives. Now, let us talk about the electrical properties of the heart. The heart generates its own electrical signals. These signals are produced by changes in the movement of ions across the cell membranes of the heart muscle cells. The movement of ions creates a flow of current, which is the basis of the electrocardiogram. The electrical signals of the heart are generated by specialized cells in the sinoatrial node. These cells have a property called automaticity. They can spontaneously generate electrical impulses without any input from the nervous system. The rate at which these impulses are generated is determined by the balance of sympathetic and parasympathetic activity. The sympathetic nervous system speeds up the rate, while the parasympathetic nervous system slows it down. The electrical impulses generated by the sinoatrial node spread through the atria, causing them to contract. They then reach the atrioventricular node, where they are delayed for a fraction of a second. This delay allows the atria to finish contracting before the ventricles begin. The impulses then travel down the bundle of His and the Purkinje fibers, spreading through the ventricles and causing them to contract. The coordinated contraction of the heart requires that the electrical impulses be conducted rapidly and uniformly through the heart muscle. If the conduction is slowed or blocked, the contraction becomes uncoordinated, and the heart's pumping efficiency is reduced. This is the basis of conduction disorders, such as heart block. Now, let us bring everything together. The physics of the heart is the physics of pressure, flow, and resistance. It is the physics of fluid dynamics and muscle contraction and electrical conduction. Understanding these principles is essential for understanding how the heart works and how it can fail. We have now covered the heart from its anatomy to its physiology, from its development to its diseases,
from the tools we use to diagnose it to the physics that governs its function. We have seen the heart as a pump, as a muscle, as an electrical generator, and as a living organ. We have traced its path through the body and through history, and we have seen how our understanding of the heart has evolved over time. The heart is a remarkable organ. It is a testament to the power of natural selection and the elegance of biological design. It is a pump that works continuously for decades without failure. It is a muscle that adapts to the demands placed on it. It is an electrical generator that produces its own signals, and it is a living organ that can be affected by disease, but can also be treated. The heart is also a symbol of life, of love, of courage. It is the organ that we associate with our deepest emotions. It is the organ that sustains us from the first beat to the last. So, as you lie there tonight, listening to the sound of your own heart, remember the physics that governs its function. Remember the pressure that drives the blood through your arteries. Remember the resistance that the vessels provide. Remember the flow that delivers oxygen and nutrients to your tissues. Remember the electrical signals that coordinate each beat. And remember that all of this is happening without any conscious effort on your part. Your heart is working for you right now. It has been working for you since before you were born. It will continue to work for you until the moment you die. And that is something worth appreciating. We have explored the heart from its anatomy to its physics, from its development to its diseases. We have traced the path of blood, understood the electrical system, seen how pressure and flow work, and learned how modern medicine diagnoses and treats heart conditions. But there is one more aspect of this story that connects everything we have learned. One more dimension that makes the heart truly remarkable. And that is its relationship with the rest of the body. Because the heart does not work in isolation. It is part of a larger system, a network of organs and tissues that all depend on each other. The heart pumps blood to the lungs to pick up oxygen. The lungs provide oxygen to the blood. The blood carries oxygen and nutrients to every cell in the body, and the cells produce waste products that the blood carries away to be eliminated. This is the circle of life, the continuous flow that sustains us from moment to moment. And understanding how the heart fits into this larger system is essential for understanding how it works and how it can fail. Let us start with the lungs. The lungs are the site of gas exchange. They take in oxygen from the air and release carbon dioxide from the blood. The right side of the heart pumps blood to the lungs through the pulmonary artery. In the lungs, the blood flows through capillaries that surround the alveoli, the tiny air sacs where gas exchange occurs. Oxygen diffuses from the alveoli into the blood, and carbon dioxide diffuses from the blood into the alveoli. The oxygenated blood then returns to the left side of the heart through the pulmonary veins. The lungs are delicate structures. They are designed for gas exchange, not for high pressure. The pressure in the pulmonary circulation is about 1/5 of the pressure in the systemic circulation. This is why the right ventricle is thinner and weaker than the left ventricle. It does not have to generate as much pressure. Now, let us think about what happens when the lungs are not working properly. If the lungs are damaged by disease, such as emphysema or pulmonary fibrosis, the exchange of oxygen and carbon dioxide is impaired. The blood does not get enough oxygen and the body becomes hypoxic. The heart has to work harder to pump blood through the damaged lungs, which can lead to right-sided heart failure. This is called cor pulmonale, and it is a serious condition. Now, let us talk about the kidneys. The kidneys are the site of waste elimination. They filter the blood, removing waste products and excess fluid, which are then excreted as urine. The kidneys also play a crucial role in regulating blood pressure. They produce a hormone called renin, which activates the renin-angiotensin system, a powerful regulator of blood pressure. They also produce erythropoietin, a hormone that stimulates the production of red blood cells. The relationship between the heart and the kidneys is a close one.
The heart pumps blood to the kidneys, and the kidneys regulate the blood volume and pressure that the heart has to pump against. If the kidneys are damaged by disease, such as chronic kidney disease, they cannot regulate blood volume and pressure effectively. This can lead to hypertension, which puts strain on the heart and can lead to heart failure. Conversely, if the heart is failing, it cannot pump blood effectively to the kidneys. The kidneys receive less blood flow, which leads to reduced urine output and the retention of fluid. This fluid retention can cause edema, swelling in the legs and lungs, which makes the heart failure worse. This is a vicious cycle that can lead to progressive decline in both heart and kidney function. Now, let us talk about the brain. The brain is the most oxygen-dependent organ in the body. It accounts for about 2% of the body's weight, but consumes about 20% of the body's oxygen.
This is because the brain is constantly active, even during sleep.
The brain cannot store oxygen, so it depends on a continuous supply from the blood. If the blood supply to the brain is interrupted for even a few minutes, brain cells begin to die. The brain receives its blood supply from the carotid and vertebral arteries, which branch off the aorta. The blood flow to the brain is carefully regulated to ensure a constant supply. The cerebral circulation has its own regulatory mechanisms that maintain blood flow even when systemic blood pressure fluctuates. This is called autoregulation. The relationship between the heart and the brain is also a close one. The brain controls the heart through the autonomic nervous system. The brainstem contains centers that regulate heart rate and blood pressure. These centers receive input from baroreceptors, which sense blood pressure, and from chemoreceptors, which sense oxygen and carbon dioxide levels.
The brain also responds to higher-level signals, such as emotions and thoughts, which can affect heart rate and blood pressure. Now, let us talk about the blood itself. Blood is not just a fluid, it is a complex tissue that contains cells and proteins. The red blood cells carry oxygen, the white blood cells fight infection, the platelets help clot the blood, and the plasma, the liquid part of the blood, contains water, proteins, hormones, and nutrients. The composition of the blood is carefully regulated. The body maintains a constant blood volume, a constant pH, a constant concentration of ions, and a constant concentration of nutrients. This regulation is essential for the proper function of all organs. The blood also plays a role in thermoregulation. By dilating or constricting the blood vessels near the skin, the body can adjust its heat loss. When the body is hot, the vessels dilate, increasing blood flow to the skin and allowing heat to escape.
When the body is cold, the vessels constrict, reducing blood flow to the skin and conserving heat. Now, let us think about what happens when the blood itself is abnormal. If the blood is too thick, it can increase the resistance to flow and put strain on the heart. This can happen in conditions such as polycythemia, where the body produces too many red blood cells. If the blood is too thin, it can lead to bleeding and anemia. This can happen in conditions such as hemophilia or thrombocytopenia. If the blood has too much cholesterol, it can lead to atherosclerosis and coronary artery disease. If the blood has too much sugar, it can damage the blood vessels and lead to diabetes complications. If the blood has too much sodium, it can increase blood volume and raise blood pressure. So, the heart does not work in isolation. It works in concert with the lungs, the kidneys, the brain, and the blood itself.
Each of these organs and tissues plays a role in maintaining the balance that sustains life.
And when one part of the system fails, the others are affected. This is why the treatment of heart disease often involves treating other organs as well. For example, A patient with heart failure may need medications that also affect the kidneys, such as diuretics, which reduce fluid retention. A patient with coronary artery disease may need medications that also affect the blood, such as statins, which lower cholesterol, or aspirin, which reduces the risk of clotting. A patient with arrhythmias may need medications that also affect the brain, such as beta blockers, which reduce the effects of sympathetic stimulation. This interconnectedness is also why prevention is so important. By taking care of the whole body, by eating a healthy diet, exercising regularly, not smoking, and managing stress, we can reduce the risk of disease in all organs. Now, let us bring everything together.
The heart is the center of the cardiovascular system, but it is not alone. It works with the lungs to deliver oxygen, with the kidneys to regulate blood volume and pressure, with the brain to coordinate the autonomic nervous system, and with the blood itself to carry nutrients and waste. The heart is a remarkable organ, but it is also part of a larger system. Understanding this system is essential for understanding how the heart works and how it can fail. And understanding this system is essential for treating heart disease effectively. We have covered a lot of ground in this series. We have explored the heart from its anatomy to its physics, from its development to its diseases. We have traced the path of blood, understood the electrical system, and seen how pressure and flow work. We have looked at the tools doctors use to diagnose heart disease, the future of cardiology, and the physics of the cardiovascular system. But there is one more chapter to write.
One more dimension to the story. And that is the story of the heart in the human experience. The heart as a symbol, as an emotion, as a metaphor. The heart as the center of our being. Because the heart is more than a pump. It is more than a muscle. It is more than an electrical generator. It is the organ that we associate with love, with courage, with life itself. It is the organ that sustains us from the first beat to the last. And it is the organ that we turn to when we want to express our deepest feelings. So as you lie there tonight, listening to the sound of your own heart, remember that you are not just hearing a pump. You are hearing the sound of life. You are hearing the sound of everything that makes you human. And that is something worth appreciating. We have now spent 10 chapters exploring the heart from every possible angle.
We have looked at its anatomy, its physiology, its electrical system, its development, its diseases, the tools we use to diagnose it, the physics that governs its function, and its relationship with the rest of the body. But there is one more dimension to this story that we have not yet fully explored. One more aspect that makes the heart truly remarkable. And that is the history of how we came to understand it. Because the story of the heart is not just a story of biology and physics, it is also a story of human curiosity, perseverance, and ingenuity. It is a story of doctors and scientists who were willing to challenge the beliefs of their time, to take risks, and to push the boundaries of knowledge. And it is a story that is still being written. Let us start with the ancient world. The ancient Egyptians, as we have seen, believed the heart was the seat of the soul. They preserved it during mummification and treated it with great reverence.
The ancient Greeks, led by Hippocrates and Aristotle, began to think about the heart in more systematic terms. They observed its structure and function, and they developed theories about how it worked. But many of their theories were based on speculation rather than observation. The most influential figure in the ancient understanding of the heart was Galen, the Greek physician who lived in the 2nd century. Galen's theories dominated medicine for more than 1,000 years. He believed that the heart was a furnace that heated the blood.
that the liver produced blood from food, and that the blood flowed outward through the veins and was consumed by the tissues. He also believed that there were invisible pores in the septum that allowed blood to pass from the right side of the heart to the left. These beliefs were wrong, but they were accepted as fact for centuries. The first challenge to Galen's authority came from the Islamic world. Ibn al-Nafis, a Syrian physician who lived in the 13th century, described the pulmonary circulation. He stated that the blood goes from the right ventricle to the lungs, where it mixes with air, and then returns to the left ventricle. He rejected the idea of pores in the septum, but his work was largely unknown in Europe until it was rediscovered in the 20th century. In Europe, the challenge to Galen's authority came from Andreas Vesalius, the Flemish anatomist who published De Humani Corporis Fabrica in 1543. Vesalius performed his own dissections and found that many of Galen's descriptions were incorrect. He showed that the human jaw is one bone, not two, as Galen had described. He showed that the human liver has only 2 lobes, not 5. And he showed that the septum of the heart is solid, with no pores. He did not directly challenge Galen's theory of circulation, but he laid the groundwork for the revolution that was to come.
The revolution came with William Harvey, the English physician who published De Motu Cordis in 1628. Harvey combined careful observation with quantitative reasoning. He measured the volume of blood pumped by the heart and showed that it was far more than the body could produce from food. He concluded that the blood circulates, flowing from the heart through the arteries and returning through the veins. Harvey's work was the foundation of modern cardiovascular physiology. But Harvey did not have the tools to see the capillaries, the tiny vessels that connect the arteries to the veins. That discovery came in 1661, when Marcello Malpighi used a microscope to observe the capillaries in a frog's lung. Malpighi's discovery completed the picture of the circulation that Harvey had described. Over the next 2 centuries, physicians and scientists continued to explore the heart and circulation. They measured blood pressure, developed the stethoscope, and began to understand the electrical activity of the heart. But many questions remained unanswered. One of the most important questions was how the heart generates its rhythm. This question was answered in the late 19th and early 20th centuries, when scientists discovered the sinoatrial node and the atrioventricular node and the conduction system. The development of the electrocardiogram in 1903 allowed doctors to record the heart's electrical activity for the first time. The 20th century brought even more advances. The development of cardiac catheterization in the 1920s and 30s allowed doctors to measure pressures inside the heart and to take blood samples from its chambers. The development of coronary angiography in the 1950s allowed doctors to see the coronary arteries. The development of echocardiography in the 1960s allowed doctors to see the heart in motion. The treatment of heart disease also advanced dramatically. The development of cardiac surgery in the 1950s allowed doctors to repair heart defects and replace damaged valves. The development of coronary artery bypass surgery in the 1960s and 70s allowed doctors to restore blood flow to the heart muscle. The development of angioplasty and stenting in the 1980s and 90s allowed doctors to open blocked arteries without open surgery. The development of medications also transformed the treatment of heart disease. The discovery of digitalis, the first effective treatment for heart failure, dates back to the 18th century. The discovery of nitroglycerin, the
The first effective treatment for angina dates back to the 19th century.
The discovery of beta blockers, ACE inhibitors, and statins in the 20th century revolutionized the treatment of heart disease. Now, let us think about what all of this means. The story of the heart is a story of progress. It is a story of how human curiosity and ingenuity have led to a deeper understanding of one of the most important organs in the body. It is a story of how we have moved from superstition to science, from speculation to observation, from ignorance to knowledge. But the story is not finished. There is still much we do not know about the heart. We do not fully understand how it develops, how it adapts, or how it fails. We do not fully understand the causes of many types of heart disease. We do not have cures for many of these diseases. The future of cardiology is bright. Advances in genetics, molecular biology, and artificial intelligence are opening up new avenues of research. New therapies, including gene therapy, stem cell therapy, and tissue engineering, are being developed. And new devices, including artificial hearts and ventricular assist devices, are being refined. But the most important advances may come from a deeper understanding of the heart itself. A deeper understanding of its structure, its function, and its regulation. A deeper understanding of how it works in health and what goes wrong in disease. A deeper understanding of the physics and the chemistry and the biology of this remarkable organ. So, let us review what we have learned in this chapter. The history of the heart is a story of progress. It is a story of how human curiosity and ingenuity have led to a deeper understanding of one of the most important organs in the body. It is a story of how we have moved from superstition to science, from speculation to observation, from ignorance to knowledge. And it is a story that is still being written. We have now covered the heart from its anatomy to its physics, from its development to its diseases, from the tools we use to diagnose it, to the history of how we came to understand it. We have traced the path of blood, understood the electrical system, and seen how pressure and flow work. We have looked at the relationship between the heart and the rest of the body. And we have seen how the heart fits into the larger story of human knowledge. The heart is a remarkable organ. It is a pump that works continuously for decades. It is a muscle that adapts to the demands placed on it. It is an electrical generator that produces its own signals. It is a symbol of life, of love, of courage. And it is a testament to the power of human curiosity and ingenuity. So, as you lie there tonight, listening to the sound of your own heart, remember that you are hearing more than just a pump. You are hearing the result of thousands of years of human inquiry. You are hearing the sound of progress. And that is something worth appreciating. But we are not quite finished. There is still one more chapter to write, one more dimension to the story, and that is the story of the heart in the future. What will the next 50 years bring? How will our understanding of the heart continue to evolve? And how will these advances change the way we live and die? We will explore these questions in the next chapter. We will look at the cutting-edge research that is happening right now. We will see how genetics, artificial intelligence, and regenerative medicine are transforming the field of cardiology. And we will imagine what the future might hold. So, let us continue this journey together. Let us explore the future of the heart. And let us appreciate the miracle that beats inside your chest every second of every day. We have now journeyed through the heart from its earliest beginnings to the present day. We have explored its anatomy, its physiology, its electrical system, its development, its diseases, the tools we use to diagnose it, the physics that governs its function, its relationship with the rest of the body, and the history of how we came to understand it. But now it is time to look forward. It is time to imagine the future of the heart. What will the next 50 years bring? How will our understanding of the heart continue to evolve? And how will these advances change the way we live and die? These are the questions we will explore in this chapter. The future of cardiology is being shaped by several powerful forces. Advances in genetics and molecular biology are revealing the genetic basis of heart disease. Advances in material science and engineering are leading to new devices and treatments. And advances in data science and artificial intelligence are enabling new ways of analyzing and interpreting information. Let us start with genetics.
Over the past 2 decades, scientists have identified dozens of genes that increase the risk of heart disease. These genes affect cholesterol metabolism, blood pressure regulation, inflammation, and many other pathways. Understanding these genes is leading to new therapies that target specific pathways. One of the most exciting developments is the use of gene editing to treat inherited heart diseases. Gene editing technologies, such as CRISPR, allow scientists to precisely modify DNA. In the future, it may be possible to correct the genetic mutations that cause diseases such as hypertrophic cardiomyopathy, long QT syndrome, and familial hypercholesterolemia. These are diseases that affect thousands of people and can cause sudden death at a young age. Another area of research is the use of gene therapy to treat acquired heart diseases. Gene therapy involves introducing a healthy copy of a gene into the body to compensate for a defective one.
In the future, it may be possible to use gene therapy to treat heart failure by introducing genes that promote the growth of new blood vessels or that protect the heart muscle from injury. Now, let us talk about stem cells. Stem cells are undifferentiated cells that can develop into different types of cells. Scientists are exploring the use of stem cells to repair damaged heart muscle after a heart attack. The idea is to inject stem cells into the heart, where they could potentially differentiate into new heart muscle cells and restore function. While early clinical trials have shown mixed results, the research is ongoing and holds promise. One of the challenges of stem cell therapy is that the heart muscle cells, or cardiomyocytes, do not divide. Once they are damaged, they are gone. But stem cells could potentially replace them.
The hope is that stem cell therapy could one day be used to repair the damage caused by a heart attack, restoring the heart's function and preventing heart failure. Another area of research is tissue engineering. Scientists are growing heart tissue in the laboratory, using scaffolds to create 3-dimensional structures that resemble the heart. These engineered tissues could eventually be used to patch damaged areas of the heart, or even to create whole organs for transplantation. The goal is to create a functional heart that could be transplanted into a patient with end-stage heart failure. Now, let us talk about devices. The field of cardiovascular devices has advanced dramatically over the past few decades. Pacemakers, implantable defibrillators, and ventricular assist devices have become smaller, more reliable, and more sophisticated.
The latest generation of these devices can communicate wirelessly with monitoring systems, allowing physicians to track a patient's heart rhythm and device function remotely. One of the most exciting developments is the artificial heart. The total artificial heart, a device that replaces the entire heart, has been implanted in a small number of patients. While the early devices were bulky and had limited durability, newer designs are smaller, more efficient, and more durable. The goal is to create a device that can replace a failing heart for years or even decades. Another area of progress is in cardiac imaging. The imaging tools we discussed in an earlier chapter continue to improve. Higher resolution, faster scanning times, and more sophisticated image processing are enabling more accurate diagnosis and better treatment planning. In the future, it may be possible to image the heart in real time during exercise or other activities,
to assess its function more accurately.
Artificial intelligence is also transforming cardiology. AI algorithms can analyze large data sets of medical images and identify patterns that may be missed by human observers. These algorithms can help detect abnormalities on echocardiograms, CT scans, and MRI scans. They can also predict outcomes, such as the risk of a heart attack or the likelihood of response to treatment. AI is also being used to analyze wearable device data. Millions of people now wear smartwatches and fitness trackers that can monitor heart rate, physical activity, and even detect atrial fibrillation. This data is being used to identify individuals at risk and to track the effectiveness of treatments. In the future, wearable devices could become even more sophisticated, monitoring not just heart rate, but also blood pressure, oxygen saturation, and even the electrical activity of the heart. Now let us talk about prevention. The future of cardiology is not just about treating heart disease,
It is about preventing it. And this requires a shift in focus from the individual to the population. We already know the major risk factors for heart disease: high blood pressure, high cholesterol, smoking, diabetes, obesity, and physical inactivity. We know how to reduce these risk factors through lifestyle changes and medications, but we have not been successful at implementing these measures at a population level. The challenge is to change behaviors, to encourage people to eat healthier, exercise more, and stop smoking, to make healthy choices the easy choices. This requires public health interventions, policy changes, and education. It also requires addressing the social determinants of health, the conditions in which people are born, grow, live, work, and age. People with lower socioeconomic status have higher rates of heart disease. This is not just a matter of access to healthcare, it is about the environments in which people live, the stress they experience, the food they have access to, and the opportunities they have for physical activity. Addressing these social determinants will require a coordinated effort across multiple sectors: healthcare, education, housing, transportation, and urban planning. It is a complex challenge, but it is one that we must meet if we are to reduce the burden of heart disease. Now, let us look at some of the more futuristic areas of research. One area is the use of nanotechnology to deliver drugs to the heart. Nanoparticles are tiny particles that can be engineered to carry drugs and target specific tissues. In the future, it may be possible to use nanoparticles to deliver drugs directly to the heart muscle, reducing the side effects of systemic drug therapy. Another area is the use of the microbiome. The microbiome is the collection of bacteria and other microorganisms that live in our bodies.
The microbiome has been linked to many diseases, including heart disease. Understanding how the microbiome affects the heart and blood vessels could lead to new therapies that target the microbiome. And then there is the field of synthetic biology. Synthetic biology involves designing and constructing new biological systems. In the future, scientists may be able to engineer cells that can produce therapeutic molecules, such as growth factors or hormones, in response to specific signals. These engineered cells could be implanted in the heart or elsewhere to treat disease. Now, let us bring everything together. The future of cardiology is bright. Advances in genetics, stem cells, tissue engineering, devices, imaging, artificial intelligence, and prevention are all contributing to a deeper understanding and better treatment of heart disease. But there are also challenges. The cost of new therapies and technologies is high. The complexity of the heart and circulation is immense, and the burden of heart disease is enormous. Heart disease remains the leading cause of death in the United States and around the world. The goal of all these advances is to reduce the burden of heart disease, to extend lives, and to improve the quality of life for patients. And while we have made tremendous progress, there is still much work to be done. So what will the next 50 years bring? It is impossible to predict with certainty, but it is likely that we will see continued progress in genetics, stem cells, devices, imaging, and artificial intelligence. It is likely that we will see new therapies for heart disease, including gene therapy, stem cell therapy, and tissue engineering. And it is likely that we will see new approaches to prevention, including public health interventions and social policies that address the root causes of disease. But the most important thing we can do is to continue to learn, to continue to ask questions,
to continue to push the boundaries of knowledge. Because the heart is a remarkable organ, and there is still much we do not know about it. We have now covered the heart from its anatomy to its physics, from its development to its diseases, from the tools we use to diagnose it to the history of how we came to understand it, to the future of cardiology. We have traced the path of blood, understood the electrical system, and seen how pressure and flow work. We have looked at the relationship between the heart and the rest of the body, and we have imagined what the future might hold. The heart is a remarkable organ. It is a pump that works continuously for decades. It is a muscle that adapts to the demands placed on it. It is an electrical generator that produces its own signals. It is a symbol of life, of love, of courage, and it is a testament to the power of human curiosity and ingenuity. So, as you lie there tonight, listening to the sound of your own heart, remember that you are hearing more than just a pump. You are hearing the result of billions of years of evolution. You are hearing the result of thousands of years of human inquiry. And you are hearing the promise of a future filled with new discoveries and new treatments. Your heart is working for you right now. It has been working for you since before you were born. It will continue to work for you until the moment you die. And that is something worth appreciating. We have now traveled through 12 chapters exploring the heart from every possible angle. We have traced its anatomy, its physiology, its electrical system, its development, its diseases, the tools we use to diagnose it, the physics that governs its function, its relationship with the rest of the body, the history of how we came to understand it, and the future of cardiology. Now it is time for the final chapter. The chapter that brings everything together. The chapter that reminds us why all of this matters. Because the heart is more than just an organ. It is more than just a pump. It is more than just a muscle or an electrical generator. It is the center of our being. It is the symbol of life itself. And understanding how it works is understanding something fundamental about what it means to be human. Let us start by reflecting on everything we have learned. We have learned that the heart is a four-chambered pump that moves blood through two separate circuits, the pulmonary circulation and the systemic circulation. We have learned that the right side of the heart pumps blood to the lungs, where it picks up oxygen and releases carbon dioxide. We have learned that the left side of the heart pumps blood to the rest of the body, delivering oxygen and nutrients to every cell. We have learned that the heart has 4 valves that ensure blood flows in only one direction. The tricuspid and mitral valves control flow between the atria and ventricles. The pulmonary and aortic valves control flow from the ventricles into the arteries. These valves open and close passively, driven by pressure differences, and they do so about 100,000 times a day without wearing out. We have learned that the heart generates its own electrical signals. The sinoatrial node, the natural pacemaker, initiates each heartbeat. The electrical signal spreads through the atria, is delayed at the atrioventricular node, and then spreads through the ventricles via the bundle of His and the Purkinje fibers. This coordinated sequence ensures that the atria contract before the ventricles, maximizing the efficiency of the pump. we have learned that the heart has its own blood supply. The coronary arteries branch off the aorta immediately after it leaves the heart. They deliver oxygen and nutrients to the heart muscle. Blood flow to the heart muscle occurs primarily during diastole, when the heart is relaxed and the vessels are not compressed. We have learned that the heart is regulated by the nervous system, by hormones, and by local signals. The sympathetic nervous system speeds up the heart and increases its force of contraction. The parasympathetic nervous system slows the heart down. Hormones such as epinephrine and angiotensin II affect heart rate and blood pressure, and local signals such as adenosine and carbon dioxide regulate blood flow to individual organs. We have learned that the heart can fail. Coronary artery disease, heart failure, arrhythmias, and valvular disease are all common conditions that can affect the heart. These diseases develop over years, often decades, and are influenced by genetics, lifestyle, and environment. But we have also learned that these diseases can be prevented and treated. Lifestyle changes, medications, and procedures such as angioplasty and bypass surgery can all help. We have learned that we can see inside the heart. The stethoscope, the electrocardiogram, the echocardiogram, cardiac catheterization, nuclear imaging, MRI and CT all allow us to visualize the heart and its function. These tools have transformed the diagnosis and treatment of heart disease. We have learned about the physics of the heart. Pressure, flow, and resistance are the fundamental principles that govern the circulation. The heart generates pressure, the vessels provide resistance, and blood flows from areas of high pressure to areas of low pressure. The Frank-Starling law ensures that the heart pumps all the blood that returns to it. We have learned that the heart does not work in isolation. It works with the lungs, the kidneys, the brain, and the blood itself. Each of these organs and tissues plays a role in maintaining the balance that sustains life. And when one part of the system fails, the others are affected. We have learned the history of how we came to understand the heart. From the ancient Egyptians to Galen to Vesalius to Harvey to the present day, the story of the heart is a story of progress. It is a story of how human curiosity and ingenuity have led to a deeper understanding of one of the most important organs in the body. And we have looked to the future. Advances in genetics, stem cells, tissue engineering, devices, imaging, artificial intelligence, and prevention are all contributing to a deeper understanding and better treatment of heart disease. Now, let us bring everything together. What does all of this mean? What is the take-home message? The take-home message is this. The heart is a remarkable organ. It is a pump that works continuously for decades without failure. It is a muscle that adapts to the demands placed on it. It is an electrical generator that produces its own signals.
It is regulated by a complex network of nervous and hormonal signals. It has its own blood supply. It can be affected by disease, but it can also be prevented and treated. But the heart is more than just an organ. It is a symbol of life, of love, of courage. It is the organ that we associate with our deepest emotions. When we say heart, we mean something more than just a pump. We mean the essence of who we are. Think about the language we use. We say heartbreak when we are sad. We say heartwarming when we are moved. We say learn by heart when we memorize something deeply. We say heart of gold when we describe someone kind. We say follow your heart when we encourage someone to trust their feelings. The heart is woven into our language, our culture, and our identity. And there is a reason for this. The heart is the first organ to function in the developing embryo. It is the organ that sustains us from before we are born until the moment we die. It is the organ that we can feel beating in our chest when we are scared, excited, or in love. It is the organ that connects us to the world, that responds to our emotions, that keeps us alive. The heart is also a source of wonder. It is a pump that works without any conscious effort on our part. It is a muscle that never gets tired. It is an electrical system that generates its own signals. It is a testament to the power of evolution and the elegance of biological design. And the heart is a source of hope. Because even though heart disease is the leading cause of death in the United States and around the world, we have made tremendous progress in preventing and treating it. We have developed medications that lower cholesterol and blood pressure. We have developed procedures that open blocked arteries and replace damaged valves. We have developed devices that regulate the heart's rhythm and support its function.
We have developed tools that allow us to see inside the heart and diagnose its diseases. And the progress continues. Advances in genetics, stem cells, tissue engineering, devices, imaging, and artificial intelligence are all opening up new avenues for prevention and treatment. The future of cardiology is bright. But the most important thing we can do is to take care of our hearts, to eat a healthy diet, to exercise regularly, to not smoke, to manage stress, and to get regular checkups, to know our blood pressure and cholesterol numbers, to be aware of the warning signs of a heart attack, and to seek help immediately if we experience them. Because the heart is precious. It is the organ that sustains us. It is the organ that connects us to the world. And it is the organ that we must protect. So, as you lie there tonight, listening to the sound of your own heart, remember everything we have learned together. Remember the 4 chambers and the 4 valves. Remember the coronary arteries and the conduction system. Remember the regulation of blood pressure and the exchange of oxygen and nutrients in the capillaries. Remember the journey of a single red blood cell from the left ventricle through the aorta, through the arteries and arterioles, into the capillaries, back through the venules and veins, and into the right atrium. Remember the millions of such journeys that happen every single minute of every single day. Remember that your heart has been beating without interruption since before you were born. Remember that it will continue to beat until the moment you die. And remember that you are the heart. Not just the muscle, but the life that it sustains. You are the reason it beats. You are the reason it never stops. And that is something worth appreciating. We have come to the end of our journey together.
We have explored the heart from its anatomy to its physics, from its development to its diseases, from the tools we use to diagnose it to the future of cardiology. We have traced the path of blood, understood the electrical system, and seen how pressure and flow work. We have looked at the relationship between the heart and the rest of the body. We have learned the history of how we came to understand the heart. And we have looked to the future. The heart is a remarkable organ. It is the most reliable pump in the known universe. It works continuously for decades without failure. It adapts to the demands placed on it. It is regulated by a complex network of signals. It has its own blood supply. It can be affected by disease, but it can also be treated. And it has a limited ability to heal itself. But the heart is also a symbol of life, of love, of courage. It is the organ that we associate with our deepest emotions.
It is the organ that sustains us, from the first beat to the last. So, the next time you feel your pulse, remember everything you have learned. Remember that you are not just feeling a muscle contract. You are feeling the result of billions of years of evolution. You are feeling the result of thousands of years of human inquiry. You are feeling the promise of a future filled with new discoveries and new treatments. And remember that your heart is working for you right now. It has been working for you since before you were born. It will continue to work for you until the moment you die. And that is something worth appreciating. Thank you for joining me on this journey through the heart. I hope you have learned something new, something that has changed the way you think about this remarkable organ. And I hope that the next time you hear your own heartbeat, you will listen to it with a new appreciation for the miracle that it represents. We have come to the end of our journey. 13 chapters, thousands of words, countless discoveries. We have explored the heart from its earliest beginnings to the furthest reaches of its future. We have traced the path of blood, understood the electrical system, seen how pressure and flow work, and learned how modern medicine diagnoses and treats heart conditions. We have looked at the relationship between the heart and the rest of the body, learned the history of how we came to understand it, and imagined what the future might hold. But now it is time to bring everything together. It is time to reflect on what we have learned and to appreciate the heart for what it truly is. The heart is a remarkable organ. It is a pump that works continuously for decades without failure. It is a muscle that adapts to the demands placed on it. It is an electrical generator that produces its own signals. It is a living tissue that can be affected by disease, but can also be treated. It is a symbol of life, of love, of courage.
And it is a testament to the power of evolution and the elegance of biological design. Think about what we have learned about the heart's structure. The 4 chambers, the 2 atria and the 2 ventricles, working together as a double pump. The right side sending blood to the lungs, the left side sending blood to the rest of the body. The valves ensuring that blood flows in only one direction. The coronary arteries providing the heart with its own blood supply. The conduction system, generating and spreading the electrical signals that coordinate each beat. Think about what we have learned about the heart's function. How it generates pressure to drive blood through the circulation. How it adapts to changes in demand, increasing its rate and force of contraction during exercise or stress. How it regulates its output to match the venous return, thanks to the Frank-Starling mechanism. How it responds to nervous and hormonal signals, speeding up when you are scared and slowing down when you are relaxed. Think about what we have learned about the circulation. The arteries carrying blood away from the heart, the capillaries where exchange occurs, the veins returning blood to the heart. The systemic circulation delivering oxygen and nutrients to every cell in the body. The pulmonary circulation picking up oxygen and releasing carbon dioxide. The 60,000 miles of vessels that form the network of life. Think about what we have learned about the physics of the heart. Pressure, flow, and resistance. The relationship between these 3 variables that governs the entire circulation. The importance of blood pressure in determining flow. The role of the arterioles in regulating resistance. The way the heart's elasticity maintains continuous flow even during diastole. Think about what we have learned about the diseases of the heart. Coronary artery disease, caused by the buildup of plaque in the coronary arteries. Heart failure, when the heart cannot pump enough blood to meet the needs of the body. Arrhythmias, disorders of the heart's rhythm. Valvular disease, when the valves become narrowed or leaky. These diseases affect millions of people around the world. But we have also learned that they can be prevented and treated. Think about what we have learned about the diagnosis of heart disease. The stethoscope, the electrocardiogram, the echocardiogram, cardiac catheterization, nuclear imaging, MRI, and CT. These tools have transformed the way we see the heart. They allow us to detect disease early, to plan treatment, and to monitor progress. Think about what we have learned about the treatment of heart disease. Lifestyle changes, medications, procedures, and surgeries. Statins to lower cholesterol. ACE inhibitors to lower blood pressure. Beta blockers to reduce the workload on the heart.
Angioplasty and stenting to open blocked arteries. Bypass surgery to restore blood flow. Valve replacement to correct valvular disease. Pacemakers and defibrillators to regulate the heart's rhythm. Think about what we have learned about the future of cardiology. Genetics, stem cells, tissue engineering, devices, imaging, artificial intelligence, and prevention. These are the forces that are shaping the future of heart care. They hold the promise of new therapies, better outcomes, and longer lives. And think about what we have learned about the history of the heart. From the ancient Egyptians to Galen to Vesalius to Harvey to the present day. The story of the heart is a story of progress. It is a story of how human curiosity and ingenuity have led to a deeper understanding of one of the most important organs in the body. But the heart is more than just an organ. It is more than just a pump. It is more than just a muscle or an electrical generator. It is the center of our being. It is the symbol of life itself. It is the organ that we associate with our deepest emotions. When we say heart, we mean something more than just a biological structure. We mean the essence of who we are. Think about the language we use. We say heartbreak when we are sad. We say heartwarming when we are moved. We say learn by heart when we memorize something deeply. We say heart of gold when we describe someone kind. We say follow your heart when we encourage someone to trust their feelings. We say home is where the heart is. We say the heart wants what it wants. The heart is woven into our language, our culture, and our identity. And there is a reason for this. The heart is the first organ to function in the developing embryo. It starts beating at about 3 weeks after conception, before the mother even knows she is pregnant. It is the organ that sustains us from before we are born until the moment we die. It is the organ that we can feel beating in our chest when we are scared, excited, or in love. It is the organ that connects us to the world, that responds to our emotions, that keeps us alive. The heart is also a source of wonder. It is a pump that works without any conscious effort on our part. It is a muscle that never gets tired. It is an electrical system that generates its own signals. It is a testament to the power of evolution and the elegance of biological design. And the heart is a source of hope. Because even though heart disease is the leading cause of death in the United States and around the world, we have made tremendous progress in preventing and treating it. We have developed medications that lower cholesterol and blood pressure. We have developed procedures that open blocked arteries and replace damaged valves. We have developed devices that regulate the heart's rhythm and support its function.
We have developed tools that allow us to see inside the heart and diagnose its diseases. And the progress continues. Advances in genetics, stem cells, tissue engineering, devices, imaging, and artificial intelligence are all opening up new avenues for prevention and treatment. The future of cardiology is bright, but the most important thing we can do is to take care of our hearts, to eat a healthy diet, to exercise regularly, to not smoke, to manage stress, and to get regular checkups, to know our blood pressure and cholesterol numbers, to be aware of the warning signs of a heart attack, and to seek help immediately if we experience them. Because the heart is precious. It is the organ that sustains us. It is the organ that connects us to the world. And it is the organ that we must protect. So, as you lie there tonight, listening to the sound of your own heart, remember everything we have learned together. Remember the 4 chambers and the 4 valves.
Remember the coronary arteries and the conduction system. Remember the regulation of blood pressure and the exchange of oxygen and nutrients in the capillaries. Remember the journey of a single red blood cell from the left ventricle through the aorta, through the arteries and arterioles, into the capillaries, back through the venules and veins, and into the right atrium. Remember the millions of such journeys that happen every single minute of every single day. Remember that your heart has been beating without interruption since before you were born. Remember that it will continue to beat until the moment you die. And remember that you are the heart. Not just the muscle, but the life that it sustains. You are the reason it beats. You are the reason it never stops. So, let that thought settle. Let it be soft and quiet like the steady rhythm of your own heartbeat. The heart is strange, and it is beautiful, and it is yours. Every beat is a reminder that you are alive.
Every beat is a connection to the world around you. Every beat is a gift. And tonight, you do not need to solve any of it. You do not need to remember every detail. You just need to appreciate the miracle that beats inside your chest. You just need to rest. So let the questions drift. Let the details fade. Let the knowledge settle into the background. And let yourself gently, quietly fall asleep, knowing that your heart will be there when you wake up, just as it has always been.